Somewhere in the Milky Way, approximately 40 light-years from where you are resting right now, a star called Proxima Centauri is burning. It has been burning for approximately 4.5 billion years. It burned before the Earth had continents. It burned before the oceans formed. It burned before the first self-replicating molecule assembled itself in some warm shallow pool and began the chain of events that eventually produced every living thing that has ever existed on this planet, including you. And when the sun exhausts its hydrogen fuel 5 billion years from now and swells into a red giant that renders the Earth uninhabitable, Proxima Centauri will still be burning. When the sun's remnant white dwarf has cooled to a black dwarf over hundreds of billions of years, Proxima Centauri will still be burning. When the Milky Way is merged with Andromeda and the merged galaxy Milkomeda has aged into a quiet elliptical, Proxima Centauri will still be burning. It will burn for approximately 4 trillion years in total, nearly 300 times longer than the current age of the universe, a span of time so vast that the sun's entire 10 billion year lifetime fits into it the way a single afternoon fits into a human life. Proxima Centauri is a red dwarf star. The smallest, coolest, dimmest, most numerous, and most long-lived type of true star in the universe. So faint that despite being the closest star to the sun, it is completely invisible to the naked eye. So small that it contains only 1/8 of the sun's mass. So cool that its surface glows not the yellow-white of the sun but a deep, ruddy red, the color of cooling embers rather than open flame. And so extraordinarily, incomprehensibly patient. For the next 3 hours, the red dwarfs are our subject. Not the brilliant supergiants that blaze for a few million years and die in spectacular explosions. Not the sun-like stars that burn for 10 billion years and swell into red giants and leave white dwarfs. The small ones. The dim ones. The ones that burn so slowly and so carefully that they will outlast everything else in the universe by a margin that makes the word outlast seem inadequate. There is something deeply restful about the red dwarfs. Something in their patience, their economy, their refusal to hurry, their burning of fuel at a rate so conservative it borders on the philosophical, that invites a particular quality of attention. A slowing of the breath. A settling into the long view. That is the view we are taking tonight. The long view. The red view. The patient view. Let us begin. To understand the red dwarfs, we need to understand first what a star is, and then what makes a red dwarf the particular kind of star it is, and then why those particular characteristics produce the extraordinary combination of properties that makes red dwarfs the most important type of star in the universe's long future, even as they are, in the present moment, among its least celebrated. A star is a self-gravitating ball of plasma, primarily hydrogen and helium, massive enough that the temperature and pressure at its center are sufficient to sustain nuclear fusion. The fusion of hydrogen nuclei into helium releases energy, and that energy, working its way outward through the star's interior, provides the pressure support that prevents the star from collapsing under its own gravity. The star is, in the most fundamental physical sense, a balance between two forces, gravity trying to compress it inward and the pressure from nuclear energy trying to expand it outward. As long as the nuclear fuel holds out and the balance is maintained, the star is in a state called hydrostatic equilibrium, and it is said to be on the main sequence, the long stable phase of its life during which it burns hydrogen in its core. the properties of a star on the main sequence are almost entirely determined by a single parameter: its mass. More massive stars are larger, hotter, more luminous, and shorter-lived. Less massive stars are smaller, cooler, dimmer, and longer-lived. The relationship between mass and luminosity is steep and nonlinear. A star twice as massive as the Sun is not twice as luminous but roughly 10 times as luminous. A star half as massive as the Sun is not half as luminous but roughly 1/10 as luminous. Mass determines almost everything about a star's character, and the range of stellar masses in the universe spans roughly 3 orders of magnitude, from approximately 8% of the solar mass to approximately 200 solar masses or more. Red dwarfs occupy the low end of this mass range. The formal definition varies somewhat depending on the source, but red dwarfs are generally understood to be stars with masses between approximately 8% and 50% of the solar mass, corresponding to spectral types M on the standard stellar classification system, and occasionally the cooler K dwarfs at the upper end of the range. The 8% lower limit is not arbitrary. It is the minimum mass required to sustain the proton-proton chain reaction, the nuclear fusion process that converts hydrogen to helium in the cores of low-mass stars, at a sufficient rate to provide the luminosity and pressure that define a true star. Below this limit, the object is a brown dwarf, capable of some fusion reactions briefly but not of sustained hydrogen burning. Above the 50% upper limit, the star's properties begin to differ significantly from the canonical red dwarf in ways that justify separating it into the K dwarf or orange dwarf category. Red dwarfs are, by a wide margin, the most common type of star in the universe. In the solar neighborhood, within roughly 30 light-years of the Sun, approximately 75% of all stars are red dwarfs. In the Milky Way as a whole, the fraction is similar or slightly higher, with estimates ranging from 70 to 80% of the total stellar population. In other galaxies, the red dwarf fraction depends on the galaxy's star formation history and initial mass function, but in typical spiral and elliptical galaxies it is comparable. The Milky Way contains approximately 200 to 400 billion stars, depending on the method of estimation. If 75% of these are red dwarfs, the galaxy contains roughly 150 to 300 billion red dwarf stars. The observable universe, with its estimated 2 trillion galaxies, contains on the order of 10 to the 23rd stars in total, of which the great majority are red dwarfs. This is a number that far exceeds the number of grains of sand on all the beaches of Earth, the number of atoms in a human body, or any other commonly invoked large number in popular scientific descriptions. Despite this extraordinary abundance, red dwarfs are essentially invisible without a telescope. The nearest star to the Sun, Proxima Centauri at 4.24 light-years distance, is a red dwarf with an apparent magnitude of approximately 11.1, far below the naked eye limit of about magnitude 6. Even the brightest red dwarfs in the sky are invisible without optical aid despite being among the nearest stars to the Sun. The sky appears to our eyes as a collection of bright, hot stars precisely because our eyes are sensitive to visible light, and red dwarfs produce most of their light in the near-infrared, at wavelengths longer than our eyes can detect. This invisibility has shaped, for centuries, our intuitions about what a typical star is. Because the stars we see are predominantly the bright, hot, short-lived ones, We have historically imagined the universe's stellar population as dominated by objects like the sun or brighter. It is only with careful, systematic surveys of the nearest stars, painstakingly correcting for the observational bias toward luminous objects, that the true picture has emerged. The universe is overwhelmingly populated by small, dim, cool, patient red dwarfs that we cannot see and have historically underappreciated. The surface temperature of a star determines its color and the distribution of its light across the electromagnetic spectrum. The Sun, with a surface temperature of approximately 5,778 Kelvin, emits most of its light in the visible range and appears yellow-white. Hotter stars, the blue and white A and B type stars, have surface temperatures of 10,000 to 30,000 Kelvin or more and emit most of their light in the blue and ultraviolet. And red dwarfs, with surface temperatures between approximately 2,400 Kelvin for the coolest M dwarfs and about 4,000 Kelvin for the warmest, emit most of their light in the red and near-infrared parts of the spectrum. The color of a red dwarf, observed with visible light instruments, ranges from deep orange to dark red depending on its temperature. The coolest red dwarfs glow with a color that is a deep, dark red, the color of a heating element just before it reaches orange, the color of the sky at the very last moment of twilight before the sun drops below the horizon. It is not the bright red of a hot ember or the brilliant crimson of a red supergiant. It is a dim, dark, brooding red, more suggestive of heat retained than heat radiated. The luminosity of red dwarfs spans an enormous range within the class. The most luminous red dwarfs, those near the upper mass boundary, have luminosities of roughly 10% of the Sun's. The least luminous, those near the hydrogen burning minimum, have luminosities of approximately 1/10,000th of the Sun's, or about 0.01%. The Sun itself is a reasonably luminous star by the standards of the overall stellar population, outshining the average red dwarf by a factor of roughly 100 to 10,000. The total light output of the Milky Way, despite being dominated numerically by red dwarfs, is overwhelmingly produced by the minority population of more massive, more luminous stars. This dimness has profound consequences for everything about the red dwarf: the distance at which a planet must orbit to receive enough warmth for liquid water, the nature of any atmosphere a planet in that orbit might sustain, the kind of photosynthesis that might operate on such a world, the character of the sky as seen from its surface, and the biology of any life forms that might evolve there. The dim light of the red dwarf shapes everything in its vicinity, and understanding that light is the first step to understanding the full world of the red dwarf system. Astronomers classify stars according to their spectral type, a system based on the absorption lines present in the star's spectrum. When the light from a star is spread out into its component wavelengths, certain wavelengths are absorbed by atoms and molecules in the star's outer atmosphere, producing dark lines at specific wavelengths that are characteristic of specific elements and molecules. The pattern of these lines identifies the star's surface temperature and chemical composition and provides an extraordinarily rich source of information about its physical properties. The spectral classification system, developed in the late 19th and early 20th centuries by Annie Jump Cannon and her colleagues at the Harvard College Observatory, organizes stars into spectral types labeled O, B, A, F, G, K, and M from hottest to coolest. The M stars, at the cool end, have surface temperatures below 4,000 Kelvin and spectra dominated by molecular absorption bands, particularly titanium oxide and vanadium oxide, that are only stable at temperatures low enough that the molecules are not torn apart by thermal radiation. Red dwarfs are predominantly M spectral type, with the coolest examples extending into the recently defined L spectral type at the boundary with brown dwarfs. Each spectral type is subdivided into 10 subtypes numbered 0 through 9, from hottest to coolest within the type. The Sun is classified as G2. Proxima Centauri is classified as M5.5, a mid to cool red dwarf. Barnard's star, the second nearest star system to the Sun, is M4. Wolf 359, one of the nearest red dwarfs and famous to science fiction enthusiasts as the location of a fictional battle, is M6.5. The cooler the number after the M, the cooler, dimmer, and smaller the star. The spectra of red dwarfs are rich with the signatures of molecules. At red dwarf surface temperatures, simple diatomic molecules such as titanium oxide, vanadium oxide, and calcium hydride are stable, and they imprint broad, distinctive absorption bands on the stellar spectrum. The presence of these molecular bands is the definitive spectroscopic signature of the M spectral type, distinguishing cool red dwarfs from the hotter stars whose spectra show only atomic absorption lines. As a red dwarf cools toward the L dwarf boundary, the molecular bands change character, with metal hydrides and eventually water vapor becoming prominent absorbers, giving the spectra of the coolest red dwarfs a distinctive appearance that differs markedly from their hotter counterparts. The solar neighborhood, the volume of space within roughly 15 to 20 light-years of the Sun, is predominantly populated by red dwarfs. Of the approximately 50 nearest known stellar systems within 12 light-years, roughly 60 to 65% are M dwarfs. This local census, the most complete and carefully studied sample of nearby stars, provides our best picture of the true composition of the stellar population, unbiased by the tendency of luminosity-limited surveys to preferentially detect the brighter, more massive stars. The three nearest star systems to the Sun illustrate the dominance of red dwarfs in the solar neighborhood well. The nearest is the Alpha Centauri system, at 4.24 to 4.37 light-years, which contains three stars: Alpha Centauri A G2 star very similar to the Sun, Alpha Centauri B, a K1 star slightly cooler and less massive than the Sun, and Proxima Centauri, an M5.5 red dwarf that is the actual nearest star at 4.24 light-years and that orbits the Alpha Centauri AB pair at an enormous distance, taking roughly 500,000 years to complete one orbit. Two of the three members of the nearest star system are therefore not red dwarfs, but the nearest individual star is. The second nearest system is Barnard's star, an M4 red dwarf at 5.96 light-years, notable as the star with the largest proper motion in the sky, moving against the background of distant stars at the remarkable rate of 10.3 arcseconds per year. Barnard's star is heading in our direction and will make its closest approach to the Sun in approximately 10,000 years, when it will be approximately 3.75 light-years away, temporarily becoming the nearest star system to the Sun. It is old, approximately 10 billion years, and has a long, interesting history in the search for extrasolar planets, with recent radial velocity surveys suggesting the possible presence of a candidate planet in a cold, distant orbit. Wolf 359, at 7.86 light-years, is one of the faintest and least massive red dwarfs in the solar neighborhood, a flare star with a mass of approximately 9% of the Sun and a luminosity of approximately 1/10,000th of the Sun's. It is so faint that even at its relatively close distance of less than 8 light-years, it requires a moderately large telescope to observe visually. And yet it will outlast the Sun by a factor of roughly 300. It is already perhaps 7 to 8 billion years old, and it has trillions of years remaining. These are our nearest neighbors. Dim, patient, long-lived, burning their fuel with a parsimony that the Sun cannot match and that we are only beginning, as astronomers and as a civilization, to properly appreciate. The red dwarfs surround us. They have always surrounded us. And they will be burning long after the Sun is gone. Tonight we learn their story. Every star in the universe begins the same way. Not in fire, but in cold. Not in brilliance, but in darkness. In the vast, frigid, and possibly diffuse clouds of molecular hydrogen and helium and trace heavy elements that drift through the interstellar medium of every galaxy, the raw material of all stars waits with the patience of geology for the conditions that will initiate the long, slow process of collapse. A molecular cloud is not the kind of cloud you see in an Earth sky. It is not a concentrated, visible, clearly bounded object. It is a region of the interstellar medium in which the gas density is high enough, and the temperature low enough, for hydrogen atoms to pair into hydrogen molecules rather than remaining as individual atoms. Molecular clouds are cold, typically between 10 and 30 Kelvin above absolute zero, colder than the surface of Pluto. They are dark, absorbing the light of background stars and giving themselves away in astronomical images as empty patches against the starfield rather than glowing structures. And they are enormous, with the largest, called giant molecular clouds, spanning hundreds of light years and containing millions of solar masses of material. It is from these cold, dark, patient structures that red dwarfs are born. Along with all other stars. Along with the brilliant blue supergiants and the yellow sun-like stars and the orange subgiants. All of them emerge from the collapse of molecular cloud material, and all of them go through essentially the same sequence of stages in their formation, differing only in the final mass they assemble and the timescale on which their formation unfolds. But the formation of a red dwarf has particular features, particular thresholds and challenges in physical constraints that distinguish it from the formation of more massive stars and that deserve careful attention. Because the red dwarf is not merely a small version of the Sun. It is a different kind of object, built by a somewhat different physical process, shaped by different forces in its formation, and emerging into its long main sequence life with a structure and character unlike any other stellar type. A molecular cloud, left entirely to itself, will not collapse. The gas pressure within it, even at its frigid temperatures, is sufficient to support the cloud against its own gravity as long as the cloud remains below a certain mass threshold called the Jeans mass. The Jeans mass, named for the British astronomer James Jeans who derived it in the early 20th century, is the critical mass above which the self-gravity of a gas cloud overcomes the thermal pressure support and collapse begins. It depends on the temperature and density of the cloud. Colder, denser clouds have lower Jeans masses and are more susceptible to collapse. In the quiet interstellar medium, most molecular cloud regions are close to the stability boundary, neither comfortably stable nor actively collapsing, held in a quasi-equilibrium by the interplay of gravity, thermal pressure, turbulence, and magnetic fields. Something must push them over the edge. Something must compress or disturb the cloud enough to initiate a runaway collapse that self-gravity then sustains. The triggers are varied. The most dramatic is the shockwave from a nearby supernova, the death explosion of a massive star, which compresses the surrounding interstellar medium with sufficient violence to push adjacent cloud regions over the Jeans instability threshold. The shockwave sweeps through the cloud, compressing the gas by factors of 10 to 100, increasing the local density dramatically and reducing the effective Jeans mass until collapse begins. The same supernova that destroys one star potentially triggers the birth of many others in the surrounding region, making star formation a self-propagating process, each generation of massive stars seeding the next through the violence of their deaths. A less dramatic but equally effective trigger is the gravitational compression experienced by a cloud region as it passes through a spiral arm. As we discussed in an earlier journey, the spiral arms of a galaxy are density waves, regions of enhanced gravitational potential that move through the galactic disk at a speed different from the orbital speed of the stars and gas. When a molecular cloud drifts into a spiral arm, the enhanced gravity of the arm compresses the cloud, triggering star formation in the compressed region. The bright young stars and glowing nebulae that trace the spiral arms of galaxies are the direct product of this arm-triggered star formation, the most recent generation of stars born in each passage of the density wave. Still other triggers include the tidal compression of cloud material and the gravitational wakes of passing massive star clusters, the accumulation of gas swept up by the expanding shells of ionized hydrogen around massive young stars, and the simple gravitational instability of cloud regions that have been cooling long enough to drop below the Jeans threshold without any external trigger at all. Star formation is, in the modern understanding, a complex, turbulent, multi-scale process with many possible initiation mechanisms, and the clouds that form red dwarfs are triggered by the same menu of mechanisms as the clouds that form all other stars. Once a region of a molecular cloud becomes Jeans unstable and begins to collapse, the process follows a characteristic sequence that has been extensively studied through computer simulations and through observations of nearby star-forming regions at multiple wavelengths. The collapse is not smooth or uniform. It is turbulent, chaotic, and hierarchical, with the large-scale collapse of the cloud region fragmenting into smaller collapses as the density increases and the local Jeans mass decreases. The earliest stages of collapse are slow. The gas is optically thin, meaning that the radiation produced by the compression can escape freely, carrying away the energy of collapse and keeping the gas cold. A cold gas has low thermal pressure and offers little resistance to gravity. The collapse accelerates. The density increases. The gas begins to fragment into multiple dense cores, each one a protostellar seed that will eventually become one or more stars. The characteristic scale of fragmentation, the typical mass of the dense cores produced, is related to the Jeans mass at the density of fragmentation, which for typical molecular cloud conditions produces cores with masses ranging from roughly 1/10 to several solar masses. A core destined to become a red dwarf is a small, cold, dense blob of gas in the fragmenting cloud, containing less than half a solar mass of material, slowly contracting under its own gravity. As it contracts, its central density increases. At some point, the gas becomes optically thick, meaning that the radiation can no longer escape freely and the collapse becomes adiabatic, The energy of contraction is retained in the gas as heat rather than being radiated away. The temperature begins to rise. The rising temperature increases the thermal pressure, which slows the collapse. A central protostellar object forms, surrounded by a collapsing envelope of gas and dust that continues to feed material onto the central core. This central core, the protostar, is not yet a star in any true sense. It is not yet fusing hydrogen. It is a dense, hot, opaque ball of gas deriving its luminosity entirely from the gravitational energy of the infalling material and from the slow contraction of its own interior. It is bright, sometimes surprisingly so for such a small object, because the conversion of gravitational potential energy to thermal radiation is an efficient process. A protostar of a few tenths of a solar mass can briefly be more luminous than its eventual main sequence luminosity, heated by the energy of accretion rather than by nuclear burning. The protostellar phase of a red dwarf's formation, the period during which the central core is accreting material from the surrounding envelope and disk, is characterized by a suite of physical processes that are qualitatively similar to those in the formation of more massive stars but that operate on different timescales and produce somewhat different outcomes. As the protostar accretes material from the surrounding cloud, the accreting gas does not fall directly onto the protostar's surface. It carries angular momentum, the rotational momentum inherited from the turbulent motions of the parent cloud, and angular momentum is conserved in the absence of external torques. The infalling gas with net angular momentum cannot reach the protostar directly but instead settles into a rotating disk around it, the protostellar disk, which mediates the transfer of material from the surrounding envelope to the protostar. Material in the disk spirals inward slowly as viscous torques and magnetic interactions transfer angular momentum outward through the disk, allowing mass to flow inward to the protostar while angular momentum flows outward. The protostellar disk around a forming red dwarf is the birthplace of any planets the star will eventually host. The dust grains in the disk collide and stick, growing from micron-sized particles to millimeter-sized aggregates to centimeter-sized pebbles to kilometer-sized planetesimals over the course of millions of years. The planetesimals interact gravitationally and collide, building up larger and larger bodies until the dominant survivors are planetary embryos, objects of roughly Mars mass, that continue to accrete material and merge with each other to produce the final planetary system. The disk around a red dwarf protostar is smaller, less massive, and cooler than the disk around a Sun-like protostar, which has important consequences for the kinds of planets that form there. Alongside the disk, the forming red dwarf drives powerful outflows. Bipolar jets of material, launched along the magnetic field lines threading the disk and star, shoot out perpendicular to the disk plane at velocities of hundreds of kilometers per second. These jets carry away some of the angular momentum that would otherwise spin the protostar up to break up velocity, and they inject energy and momentum into the surrounding molecular cloud, contributing to the turbulence that limits the efficiency of star formation and the masses of the stars that form. The jets of a forming red dwarf are less powerful than those of forming Sun-like or massive stars, scaled to the lower accretion rates and lower luminosities of the lower mass system, but they are qualitatively similar and play the same role in the overall star formation process. The duration of the protostellar phase, from the initial collapse of the dense core to the dispersal of the surrounding envelope and the emergence of the young star as a visible object, depends on the mass of the forming star. For a Sun-like star, The protostellar phase lasts roughly 100,000 years. For a red dwarf, accreting at lower rates from a less massive envelope, the phase is somewhat longer, perhaps a few 100,000 years for the least massive red dwarfs. This may seem long in human terms, but it is a tiny fraction of the eventual main sequence lifetime of the star. The most fascinating aspect of red dwarf formation is the existence of the minimum stellar mass, the boundary below which a collapsing core cannot become a true star. Understanding this boundary, what sets it and why it exists at the particular mass it does, is central to understanding the red dwarf as a class of object. As a protostellar core contracts after the dissipation of its surrounding disk and envelope, its central temperature rises. At approximately 1500 Kelvin, the molecular hydrogen in the core dissociates into atomic hydrogen, absorbing energy that would otherwise go into thermal pressure support and causing a brief acceleration of the collapse. At approximately 10,000 Kelvin, the hydrogen atoms begin to ionize, again absorbing energy. These two phases of collapse, separated by brief quasi-stable periods, eventually produce a fully ionized, plasma-state protostar whose central temperature is rising steadily as the contraction continues. In a star to be with sufficient mass, this rising central temperature will eventually reach approximately 10 million Kelvin, the threshold for the proton-proton chain reaction, the nuclear fusion process that converts hydrogen into helium and releases energy. When the central temperature reaches this threshold, nuclear burning ignites, releasing energy that increases the thermal pressure and halts the contraction. The star has found its equilibrium. The energy from nuclear fusion exactly balances the energy lost from the surface, the contraction stops, and the star settles onto the main sequence for the long, stable phase of hydrogen burning that defines its stellar existence. But for a core with mass below approximately 8% of the solar mass, something different happens. The central temperature rises as the core contracts, but it never reaches 10 million Kelvin. Instead, as the density rises to the point where the electron gas becomes degenerate, the quantum mechanical pressure of degenerate electrons begins to support the core against further contraction before the fusion temperature is reached. The contraction slows and stops, not because nuclear burning has begun, but because electron degeneracy pressure has taken over. The object settles into a quasi-equilibrium as a brown dwarf, slowly cooling over billions of years without ever igniting the sustained hydrogen fusion that defines a true star. The minimum stellar mass, the hydrogen burning limit, is therefore set by the competition between two timescales: the timescale on which the central temperature rises as the core contracts, and the timescale on which the core density rises to the point of electron degeneracy. For a core mass of roughly 8% of the solar mass, these timescales are approximately equal, and the central temperature just barely reaches the fusion threshold before degeneracy takes over. For slightly less massive cores, degeneracy wins. For more massive cores, fusion wins. The red dwarfs near the hydrogen burning limit, those with masses between 8 and 10% of the solar mass, are the stars that came closest to not being stars at all. They ignite hydrogen burning only barely, their central temperatures hovering just above the minimum required for the proton-proton chain, their luminosity so low that they are barely distinguishable from the most massive brown dwarfs by direct measurement. They are stars at the very edge of the possible, burning their fuel with an extreme parsimony that reflects their proximity to the boundary between stellar and substellar existence. After the protostellar phase ends and the surrounding envelope has been dispersed by the outflows and radiation of the central object, the young red dwarf enters a phase called the T-Tauri phase, named for the prototype young star T-Tauri in the Taurus star-forming region. The T-Tauri phase is the adolescence of a low-mass star, the period between the dissipation of the protostellar envelope and the settling of the star onto the zero-age main sequence, the initial position on the main sequence that corresponds to the star's first moment of full nuclear burning equilibrium. T-Tauri stars are characterized by strong magnetic activity, prominent emission lines in their spectra from heated chromospheric and coronal gas, rapid rotation, photometric variability from star spots and accretion hot spots, and in many cases the presence of a residual protoplanetary disk from which material continues to accrete at low rates. They are young, turbulent, magnetically active versions of what they will eventually become, and they are considerably more luminous than their eventual main sequence luminosities because they are still contracting and releasing gravitational energy in addition to any nuclear burning that may have begun. For a red dwarf, the T-Tauri phase is particularly important and particularly long. The pre-main sequence contraction timescale, the time required for a contracting protostar to reach thermal equilibrium on the main sequence, scales inversely with the star's luminosity. More massive, more luminous stars reach the main sequence quickly, within 1 million years for the most massive O and B stars. The Sun takes roughly 30 million years to reach the main sequence from its initial collapse. A red dwarf of 1/10 solar mass takes approximately 1 billion years, a timescale comparable to the entire stellar lifetime of some of the more massive stars. This extraordinarily long pre-main sequence contraction phase has an important consequence for any planets forming in the disk around a young red dwarf. For the first few 100 million to billion years of the system's history, the star is still contracting, its luminosity declining from its initial higher value toward the lower luminosity of the main sequence. The habitable zone, the range of orbital distances at which liquid water could exist on a planet's surface, is migrating inward during this period, from a larger radius during the pre-main sequence phase to a smaller radius on the main sequence. Any planet that forms within the eventual main sequence habitable zone will spend hundreds of millions of years exposed to the higher luminosity of the contracting pre-main sequence star, receiving enough energy to evaporate any water it accretes and to drive a runaway greenhouse effect that could permanently desiccate the planet's atmosphere before the star even reaches its stable main sequence state. This pre-main sequence irradiation problem is one of the most discussed challenges for habitability around red dwarfs, and we will return to it in more detail in later chapters when we examine the prospects for life in red dwarf systems. For now, it is enough to note that the long, slow path of a red dwarf to its main sequence is not merely a curiosity of stellar physics but a potential shaper of the habitability of any worlds that form in its orbit. Having traced the formation of an individual red dwarf from molecular cloud to main sequence, we are left with a question that the formation process itself raises but does not fully answer. Why are red dwarfs so much more common than massive stars? What is it about the star formation process that preferentially produces small stars over large ones? The answer is encoded in what astronomers call the initial mass function, or IMF, a description of the distribution of stellar masses produced in a typical star-forming event. The initial mass function was first characterized observationally by the Australian astronomer Edwin Salpeter in 1955, who showed that the number of stars formed at each mass is approximately proportional to the mass raised to a negative power of approximately 2.35. This is a steeply declining function. For every star formed with a mass of 10 solar masses, roughly 1,000 stars are formed with a mass of 1 solar mass, and for every Sun-like star, roughly 10 to 30 stars are formed with masses in the red dwarf range. The physical origin of the initial mass function is not fully understood, and it is one of the most actively debated topics in star formation theory. The favored explanation involves the turbulent fragmentation of molecular clouds, in which the cascade of turbulent energy from large scales to small scales produces a distribution of dense core masses that reflects the statistics of supersonic turbulence. In this picture, the most probable mass of a collapsing core, and therefore the most common stellar mass, is determined by the gene's mass at the density where turbulent fragmentation stops, which for typical molecular cloud conditions gives a characteristic mass of a few tenths of a solar mass, right in the red dwarf range. Additional physical processes, including feedback from forming stars that heat the surrounding gas and raise the local gene's mass, the magnetic braking of collapsing cores that reduces their angular momentum and affects their fragmentation, and the competitive accretion of material by forming protostellar cores in the dense cluster environment, all modify the simple turbulent fragmentation picture in ways that produce the observed initial mass function shape with reasonable fidelity. The bottom line is that red dwarfs are common because the physics of molecular cloud fragmentation preferentially produces small cores, and small cores produce small stars. The universe is structured, at the level of its fundamental star-forming processes, to create far more dim, patient red dwarfs than brilliant, short-lived massive stars. The brilliance of the night sky as we see it, dominated by hot, luminous stars, is a product of our bias toward visible light and toward bright objects. The true character of the stellar population is dim and red and patient, overwhelmingly composed of stars that our ancestors could not see and that we have only recently begun to properly appreciate. The Milky Way is, in its most honest description, a galaxy of red dwarfs, sprinkled with the occasional bright star that catches our eye. Dominated, in number and in ultimate longevity, by the small, cool, patient fires that burn all around us without our noticing. They were there when our ancestors first looked up. They are there tonight. And they will be there, burning with the same patient dim light, long after the last sun-like star has gone cold. Inside the sun, something is not happening. The innermost 30% of the sun's radius, the core and the region just above it called the radiative zone, is still. Not still in the sense of being inert or inactive, the nuclear reactions in the core are ferociously productive, fusing 600 million tons of hydrogen per second. But still in the sense of fluid dynamics. The plasma in the radiative zone does not circulate. It does not turn over. It does not mix the material in the core with the material in the outer layers. It transports the energy produced in the core outward entirely through radiation, photon by photon, with individual photons traveling microscopic distances before being absorbed and re-emitted. A random walk that takes a photon produced in the sun's core approximately 100,000 to 1 million years to complete its journey to the surface. The material itself barely moves. The composition of the radiative zone is stratified, with the helium produced by fusion accumulating in the core while the hydrogen-rich outer layers remain chemically separate. This stratification has profound consequences for the Sun's evolution. As hydrogen is consumed in the core and helium accumulates, the mean molecular weight of the core increases, requiring a higher temperature and pressure to maintain the same level of nuclear burning and hydrostatic support. The Sun's luminosity gradually increases over its main sequence lifetime as a result. The Sun today is approximately 30% more luminous than it was when it formed 4.5 billion years ago, and it will continue to brighten over the next 5 billion years until the core hydrogen is exhausted and the star's structure changes dramatically. In a red dwarf, something different is happening. The interior is not stratified and still. It is stirring, turning over, mixing. The entire interior of a fully convective red dwarf, from the nuclear burning core to the visible surface, is in a state of continuous convective overturning, with hot plasma rising from the depths and cooler plasma sinking from above in a ceaseless circulation that mixes the stellar material on timescales of years to decades. The red dwarf is, in its deep interior, more like a boiling pot than a stratified lake. This convective mixing is the single most important physical property distinguishing red dwarfs from sun-like stars. It changes everything: the lifetime of the star, the evolution of its composition, the nature of its magnetic field, the character of its surface activity, and the ultimate fate of its nuclear fuel. Understanding convection in red dwarfs is understanding the red dwarf itself. Convection is the transport of energy by the bulk motion of a fluid. When a fluid is heated from below and cooled from above, and when the temperature gradient between bottom and top exceeds a certain critical value called the adiabatic temperature gradient, the fluid becomes unstable to convective overturning. A parcel of fluid displaced slightly upward from its equilibrium position finds itself hotter and less dense than its surroundings, and therefore buoyant, and therefore continues to rise rather than returning to its original position. The instability grows, producing organized circulation cells with rising hot material in the centers and sinking cool material at the edges, transporting heat upward far more efficiently than radiation alone could manage. In the Sun, convection operates in the outer 30% of the radius, the convective envelope, where the temperature gradient is steep enough to trigger the instability. The inner 70%, including the core and radiative zone, is stable against convection and transports energy by radiation. The boundary between the radiative zone and the convective envelope, called the tachocline, is a region of sharp velocity shear and differential rotation that plays an important role in generating the Sun's magnetic field through a dynamo process. In red dwarfs, the situation is qualitatively different. For red dwarfs with masses below approximately 35% of the solar mass, the entire star is unstable to convection. There is no radiative zone. There is no tachocline. The convective envelope extends all the way from the surface down to the nuclear burning core. The photons produced by fusion in the core still contribute to energy transport, but the dominant mechanism throughout most of the star's interior is convective overturning. Hot plasma rises from the core to the surface, radiates energy, and sinks back down to be reheated. The cycle repeats continuously, on timescales of years for the deep interior and days for the outer layers. The transition between fully convective and partially radiative red dwarfs occurs at approximately 35% of the solar mass. Below this mass, full convection. Above it, and increasingly so for higher masses, a radiative core begins to develop and the star's interior structure begins to approach the Sun's stratified two-zone architecture. This transition mass is not a sharp boundary but a gradual one, with stars near the transition having convective zones that extend deep but not all the way to the center. The precise location of the transition depends on the star's metallicity, its age, and other factors that affect the opacity of the stellar interior and therefore the efficiency of radiative transport. The fully convective interior of a low-mass red dwarf is a remarkably uniform structure. Because convection mixes the stellar material so thoroughly, the composition of the interior is nearly homogeneous at any given time. The helium produced by hydrogen fusion in the core is continuously mixed outward by convection, diluted by the hydrogen-rich material being mixed downward. The hydrogen being consumed in the core is replenished by fresh hydrogen brought down from the outer layers. The star does not develop a distinct helium core the way the Sun does. Instead, the entire interior participates in the fuel supply for the nuclear reactions, and the fuel is consumed uniformly throughout the mixed volume. This has an extraordinary consequence for the red dwarf's lifetime. The Sun, with its stratified interior, can only burn the hydrogen in its core directly. As the core hydrogen is consumed, the core contracts and the shell around it heats up, eventually initiating shell burning that dramatically changes the star's structure and marks the end of the main sequence phase. The Sun has access, for main sequence burning, to only the hydrogen in its core, roughly 10% of its total hydrogen mass. The rest remains in the envelope, unavailable for fusion during the main sequence phase. A fully convective red dwarf, by contrast, has access to nearly all of its hydrogen. The convective mixing continuously replenishes the core with fresh fuel from the outer layers, allowing the entire hydrogen mass of the star to participate in the nuclear burning over the course of its main sequence lifetime. The effective fuel supply is not 10% of the stellar mass but something closer to 60 to 90%, depending on the efficiency of mixing and the fraction of the stellar mass in the deepest, hottest regions where temperatures are sufficient for fusion. This is the fundamental reason why red dwarfs live so much longer than Sun-like stars. It is not merely that they burn their fuel more slowly, though they do. It is that they have access to a much larger fraction of their total fuel supply. The combination of slow burning and complete mixing produces lifetimes that dwarf the Sun's by factors of hundreds to thousands. A red dwarf of 1/10 solar mass burns approximately 1/10,000th as much fuel per second as the Sun, but has access to a fuel supply that is comparable in fraction to the Sun's. The ratio of fuel supply to consumption rate gives the lifetime, and the ratio is prodigiously in the red dwarf's favor. The nuclear burning in a red dwarf proceeds through the same proton-proton chain that powers the Sun, but at lower temperatures and lower rates. Understanding the proton-proton chain and how it operates at the lower temperatures of red dwarf cores is essential to understanding the physics of these stars. The proton-proton chain begins when two protons, the nuclei of hydrogen atoms, collide with sufficient energy to overcome their mutual electrostatic repulsion, the Coulomb barrier, and come within range of the strong nuclear force. At this point, through a process involving the weak nuclear force, one of the protons converts to a neutron, emitting a positron and a neutrino, and the two nucleons bind together to form a deuterium nucleus. This first step is the bottleneck of the entire chain, Because the weak force process is extraordinarily rare, a given proton in the Sun's core waits, on average, approximately 10 billion years before undergoing this reaction. It is the slowness of this first step, not any shortage of protons, that determines the Sun's main sequence lifetime. After deuterium is formed, subsequent reactions proceed much more quickly. The deuterium nucleus captures another proton to form helium-3, and two helium-3 nuclei fuse to form helium-4 with the release of two protons. Each complete cycle of the proton-proton chain converts four hydrogen nuclei into one helium-4 nucleus, releasing approximately 26.7 million electron volts of energy, with a small fraction carried away by the neutrinos and the rest available to heat the stellar interior and power the star's luminosity. In red dwarf cores, the temperature is lower than in the Sun's core. The Sun's core temperature is approximately 15 million Kelvin. The core of a red dwarf of 1/10 solar mass is approximately 6 to 7 million Kelvin, barely above the fusion-ignition threshold. At these lower temperatures, the proton-proton reaction rate is dramatically lower than in the Sun, because the rate depends steeply on temperature. A factor of 2 decrease in temperature reduces the reaction rate by roughly a factor of 1,000. This is why the red dwarf's luminosity is so much lower than the Sun's. The nuclear reaction rate in its core is intrinsically much slower, producing much less energy per unit time. The temperature sensitivity of the proton-proton chain is also the physical basis for the red dwarf's remarkable self-regulating stability. If something were to slightly compress a red dwarf, raising its core temperature, the reaction rate would increase sharply, producing more energy and more pressure support, which would expand the star back to its equilibrium size. If something were to slightly expand a red dwarf, reducing its core temperature, the reaction rate would decrease, reducing the pressure support and allowing gravity to compress the star back toward equilibrium. The strong temperature sensitivity of nuclear burning provides a powerful thermostat that keeps the red dwarf structure remarkably stable over its entire main sequence lifetime. Stellar magnetic fields are generated by dynamo processes, the conversion of kinetic energy in the stellar plasma into magnetic field energy through the interaction of fluid motions with existing magnetic fields. In the Sun, the primary dynamo operates at the tachocline, the boundary layer between the radiative zone and the convective envelope, where strong velocity shear stretches and amplifies magnetic field lines in a process that generates the Sun's large-scale, roughly dipolar magnetic field with its approximately 11-year activity cycle. In fully convective red dwarfs, there is no tachocline. There is no radiative zone. There is no sharp boundary layer where velocity shear can amplify magnetic fields through the solar-type interface dynamo. For years, this absence presented a theoretical puzzle. If the solar dynamo mechanism requires a tachocline, how do fully convective red dwarfs generate magnetic fields? And yet observations showed clearly that many fully convective red dwarfs have magnetic fields of comparable or greater strength to the Sun's, and some display vigorous magnetic activity including large star spots and powerful flares. The resolution to this puzzle came from the recognition that convection itself can drive a different type of dynamo, called the distributed dynamo or convective dynamo, in which the turbulent convective motions throughout the stellar interior generate magnetic fields through the twisting and amplification of field lines by the helical convective flows. This distributed dynamo operates throughout the entire convective volume rather than at a specific boundary layer, and it can produce strong magnetic fields without any need for a tachocline. The magnetic fields of fully convective red dwarfs generated by this distributed dynamo tend to be different in character from the Sun's field. They are often predominantly axisymmetric, meaning they have a strong dipolar component aligned with the rotation axis, rather than the more complex, multipolar configurations typical of more massive convective stars. Some fully convective red dwarfs appear to have remarkably simple, stable, large-scale dipole fields that persist for years or decades without the periodic polarity reversals that characterize the solar cycle. Others show more complex time-variable fields. The magnetic behavior of red dwarfs is an active area of research, with new observational data from spectropolarimetric surveys continuously refining our understanding of how rotation rate, mass, and age interact to determine the character of the magnetic field. The strength of the magnetic field generated by the convective dynamo depends strongly on the rotation rate of the star, because faster rotation drives stronger differential rotation and stronger helical motions in the convective flows, both of which amplify the magnetic field more efficiently. Young red dwarfs, which rotate rapidly because they have not yet had time to spin down through magnetic braking, tend to have stronger magnetic fields and more vigorous magnetic activity than older, more slowly rotating red dwarfs. As a red dwarf ages and loses angular momentum to the stellar wind magnetized by its own field, its rotation rate decreases, the dynamo weakens, and the magnetic activity declines. The progression from active, rapidly rotating young red dwarf to quiet, slowly rotating old red dwarf is a gradual one, but it has important consequences for the environment experienced by any planets in the system. The energy produced by nuclear fusion in the core of a red dwarf must make its way to the surface before it can be radiated into space. In the Sun, this journey involves a trillion-year random walk through the radiative zone, followed by a much more efficient convective transit through the outer layers. In a fully convective red dwarf, the entire journey from core to surface is made by convection. Convective energy transport in a red dwarf is not instantaneous. The convective cells that carry heat from the interior to the surface have characteristic velocities that can be estimated from the mixing length theory, the standard but simplified model of stellar convection used in most stellar structure calculations. In the deep interior of a red dwarf, where the convective driving is strong and the density high, the convective velocities are relatively low, perhaps tens of meters per second. In the outer layers, where the density drops dramatically and the convective driving is more vigorous relative to the local sound speed, the convective velocities can approach and sometimes exceed the local sound speed, making the convection supersonic. The characteristic timescale for convective overturning in a red dwarf's interior, the time for a convective cell to rise from near the core to the surface and descend again, is roughly comparable to the convective turnover time, estimated at between a few days for the surface layers and a year or more for the deepest interior regions. This convective turnover time is an important parameter for understanding the stellar dynamo, because it determines the relationship between convection and rotation, specifically the Rossby number, the ratio of the rotation period to the convective turnover time, which is one of the key parameters governing magnetic activity. The efficiency of convective energy transport is so high that the temperature gradient in the interior of a fully convective red dwarf is very close to the adiabatic temperature gradient, the minimum gradient required to maintain convection. The interior is nearly adiabatically stratified, meaning that a parcel of gas displaced vertically will have almost exactly the same temperature as its new surroundings after adjusting adiabatically. This near adiabatic stratification means that the interior is only very slightly superadiabatic, only very slightly more unstable to convection than the minimum required to sustain it, and that the convective heat flux carries essentially all the energy from the core to the surface with very little excess driving. One consequence of the high efficiency of convective transport is that the interior of a red dwarf is nearly isentropic, meaning that the specific entropy is nearly uniform throughout the convective volume. This nearly uniform entropy is the thermodynamic expression of the thorough mixing that convection produces, and it is the reason why the composition of the fully convective red dwarf remains nearly homogeneous throughout its lifetime. Entropy and composition are both homogenized by the same convective mixing process, producing the uniform, well-mixed interior that is the red dwarf's most distinctive structural characteristic. For red dwarfs with masses above approximately 35% of the solar mass, the interior is no longer fully convective. A radiative core develops, occupying a central region where the temperature gradient is shallow enough that radiation can carry the energy flux without triggering convective instability. The outer layers remain convective, and the convective envelope extends from the surface downward to some depth that depends on the star's mass and metallicity, but it does not reach the center. This partially convective architecture is intermediate between the fully convective lower mass red dwarfs and the largely radiative interior of the Sun. The partially convective red dwarfs have a radiative core that grows with increasing stellar mass, accounting for an increasingly large fraction of the stellar volume, with a convective envelope sitting above it. The boundary between the radiative core and the convective envelope is not a tachocline in the solar sense, because the velocity shear is less pronounced and the geometry is different, but it is a region of compositional and thermal transition. In partially convective red dwarfs, the helium produced by fusion accumulates in the radiative core, as it does in the Sun, creating a stratification that the outer convective envelope cannot reach and mix away. The compositional gradient that develops has consequences for the star's evolution. As the radiative core grows in helium content, the mean molecular weight of the core increases, driving the gradual increase in luminosity and core temperature that characterizes main sequence evolution in partially convective stars. The partially convective red dwarfs will therefore evolve somewhat like smaller versions of the Sun, though on much longer timescales, gradually brightening and eventually developing the expanded structure of a subgiant as core hydrogen is exhausted. The transition between fully and partially convective red dwarfs at approximately 35% of a solar mass is not merely a theoretical distinction. It has observationally detectable consequences, including a change in the relationship between stellar mass and radius, a change in the character of the magnetic field from the large-scale dipole of fully convective stars to the more complex, cycle-like behavior of partially convective ones, and potentially a change in the long-term evolutionary behavior of the star. The partially convective red dwarfs, despite being less long-lived than their fully convective counterparts, are still extraordinary by any standard, with main sequence lifetimes ranging from tens of billions to hundreds of billions of years. One of the most elegant ways astronomers probe the interior structure of red dwarfs, and distinguish fully convective from partially convective stars, is through the abundance of lithium in their atmospheres. Lithium is a light element, atomic number 3, that is destroyed by nuclear reactions at temperatures above approximately 2.5 million Kelvin. In the Sun, lithium is depleted in the convective envelope because the base of the convective zone reaches temperatures high enough to destroy lithium over the Sun's lifetime. The current solar photospheric lithium abundance is roughly 100 times lower than the initial solar abundance inherited from the molecular cloud. In a fully convective red dwarf, the convective mixing carries all the stellar material, including the lithium in the outer layers, down to temperatures well above the lithium destruction threshold. The lithium is destroyed throughout the convective volume, and the photospheric lithium abundance should be very low, regardless of the star's age. In a partially convective red dwarf, if the base of the convective envelope does not reach temperatures sufficient for lithium destruction, the lithium in the outer layers can be preserved, and the photospheric abundance will reflect the initial abundance inherited from the parent molecular cloud. The lithium test, developed in the 1990s as a tool for distinguishing brown dwarfs from red dwarfs, also provides information about the internal structure of the dimmest true stars. A very low-mass red dwarf near the hydrogen burning limit that destroys all its lithium rapidly is distinguished from a brown dwarf of similar luminosity that preserves its lithium. And within the red dwarf class, the lithium abundance provides a window into the depth and efficiency of the convective mixing, an indirect probe of the internal temperature at the base of the convective zone. The interior of a red dwarf is thus not entirely hidden from view. Through the lithium abundance, through the magnetic field structure revealed by spectropolarimetry, through the oscillation modes detected by astroseismology, and through the photometric variations produced by the surface manifestations of the deep convective flows, astronomers read the interior from the outside, piecing together a picture of the red dwarf's hidden depths that grows more detailed and more nuanced with every new observational campaign. The interior stirs. Slowly. Continuously. Mixing its material over years and decades and millennia and billions of years, keeping the fuel supply replenished and the composition homogeneous and the nuclear fire burning at its patient, conservative, extraordinary rate. No stratification. No accumulating helium core. No gradual brightening towards subgiant expansion. Just the slow, steady, thorough circulation of a star that has figured out how to make its fuel last as long as the physics will allow. 1 trillion years, give or take. The surface of a red dwarf is not what you might expect. If the word surface evokes an image of calm, of stillness, of the kind of smooth boundary between star and space that appears in textbook diagrams, then a red dwarf's surface will surprise you. It is not calm. It is not still. It is a churning, turbulent, magnetically tortured boundary layer between the convective interior and the outer atmosphere, marked by enormous dark spots, by luminous bridges of plasma arching hundreds of thousands of kilometers above the photosphere along magnetic field lines, by jets of hot gas punching upward into the corona and raining back down in curtains of cooling material, by flares that release in minutes the energy the star normally radiates in days. And yet, by the standards of its own light output and its overall luminosity, the red dwarf's surface is dim. Cooler than any other stellar surface. Darker, in the sense of emitting less energy per unit area, than any other true star. The contrast between its surface dimness and its surface violence is one of the most striking things about the red dwarf, and understanding it requires understanding both the thermodynamics that sets the surface temperature and the magnetism that drives the surface activity. We begin at the photosphere, the visible surface, and work our way outward through the layers of atmosphere that extend above it, from the cool molecular layer just above the photosphere through the chromosphere and transition region to the hot, tenuous corona that extends millions of kilometers into space. The photosphere of any star is the layer from which the star's light escapes into space. Below the photosphere, the stellar plasma is opaque. Photons travel only a short distance before being absorbed and re-emitted, making the plasma effectively impenetrable to radiation on any macroscopic scale. Above the photosphere, the density drops rapidly and the plasma becomes transparent, allowing photons to travel freely outward without further absorption. The photosphere is the boundary between opaque and transparent, the layer where the last scattering of a photon before its escape into space occurs, and it is this layer that defines the visible surface of the star. In the Sun, the photosphere has a temperature of approximately 5,778 Kelvin and emits a continuous spectrum of radiation that peaks in the yellow-green part of the visible spectrum, though the integrated light appears white or slightly yellow-white due to the mixture of all visible wavelengths. The Sun's photosphere is marked by the granulation pattern, a mosaic of convective cells typically about 1,000 kilometers across, with bright centers where hot plasma is rising and darker edges where cooling plasma is sinking. These granules turn over on timescales of about 10 minutes, constantly refreshing the visible surface with new material from the convective interior below. The photosphere of a red dwarf shares the same basic physics but differs dramatically in temperature and in the nature of the material that makes up the visible layer. At temperatures between roughly 2,400 and 4,000 Kelvin, the photosphere of a red dwarf is cool enough for complex molecules to form and survive. Titanium oxide, vanadium oxide, iron hydride, magnesium hydride, calcium hydride, and water vapor are all stable at these temperatures, and they dominate the opacity and the spectral appearance of the red dwarf photosphere in ways that have no analog in hotter stellar atmospheres. The absorption of photons by these molecular species imprints the characteristic broad molecular bands on the red dwarf spectrum, giving it the distinctive reddish appearance and the rich spectral structure that sets it apart from the cleaner atomic spectra of hotter stars. The granulation pattern on a red dwarf photosphere is expected to be different from the Sun's in character and scale. Because the surface gravity of a red dwarf is higher than the Sun's, and because the convective velocities are lower due to the lower luminosity and the higher opacity of the cool photospheric gas, the granulation cells are expected to be smaller in absolute size relative to the stellar radius but larger relative to the stellar radius than solar granules, covering a larger fraction of the stellar surface at any given time. The surfaces of red dwarfs have not been spatially resolved by any current telescope, their angular diameters being far too small even for the nearest examples, but indirect evidence from photometric and spectroscopic variability is consistent with a granulation structure broadly similar to the Sun's but appropriately scaled for the red dwarf's physical parameters. One of the most striking surface features of many red dwarfs is the presence of large star spots, dark regions of the photosphere where the local magnetic field is strong enough to inhibit convection and reduce the local temperature below the surrounding photospheric value. Star spots on red dwarfs are the analogs of sunspots. The dark patches on the solar photosphere that have been observed since antiquity and that have been understood since the early 20th century as regions of concentrated magnetic field threading the solar convective envelope. In the Sun, sunspots are regions where the magnetic field strength is high enough, typically several thousand Gauss, to suppress the convective overturning that would otherwise carry heat upward from below. The suppressed convection means less heat delivery to the surface in the sunspot region, so the surface temperature there is lower than the surrounding photosphere, typically by 1000 to 2000 Kelvin. The lower temperature means lower emitted luminosity per unit area, making the sunspot appear dark against the brighter surrounding photosphere. Individual solar sunspots range in size from a few hundred to tens of thousands of kilometers, and they typically last from days to months. On red dwarfs, the starspot phenomenon is qualitatively similar but can be dramatically larger in fractional area coverage. While sunspots rarely cover more than a fraction of a percent of the solar disk at solar maximum, star spots on active red dwarfs can cover 10, 20, or even 50% of the stellar surface. These enormous spot coverages produce correspondingly large photometric variations as the star rotates and carries the spotted regions in and out of view, variations that are routinely detected by photometric monitoring surveys and that are one of the primary tools for measuring red dwarf rotation periods. The physical reason why red dwarfs can sustain such large spot coverages relative to the Sun is connected to their fully convective interiors and the character of the magnetic dynamo they drive. The large-scale, predominantly dipolar magnetic fields of fully convective red dwarfs can thread large fractions of the stellar surface simultaneously, producing coherent spot groups that persist for months to years. Some red dwarfs show evidence for nearly polar spot concentrations, with large spots located near the rotation poles rather than at the low latitudes where solar sunspots preferentially form. The geometry of the magnetic field in fully convective stars apparently favors polar spot formation in ways that the solar interface dynamo does not. The temperature contrast between a star spot and the surrounding photosphere on a red dwarf is typically smaller in absolute terms than for solar sunspots, because the photospheric temperature is already so low that a proportionally similar temperature reduction produces a smaller absolute temperature difference. But the optical contrast can be significant, and at certain wavelengths, particularly in the infrared where the star emits most of its light, the spots can produce substantial variability. Detailed modeling of red dwarf star spot properties has revealed a range of spot temperatures from a few hundred to over 1000 Kelvin below the surrounding photosphere, varying with the star's activity level and the strength of the local magnetic field. Above the photosphere, the temperature of a stellar atmosphere might be expected to decline monotonically as the distance from the energy-producing interior increases. And indeed, in the photosphere itself, the temperature does decline with height, from the base of the photosphere to the temperature minimum at the top of the photosphere where the temperature reaches its lowest value before reversing course. What happens above the temperature minimum is one of the most puzzling and most actively studied phenomena in stellar physics. The temperature increases rapidly through the chromosphere, the layer of stellar atmosphere above the photosphere. The temperature rises from the photospheric minimum of perhaps 3000 to 4000 Kelvin for a red dwarf to tens of thousands of Kelvin at the top of the chromosphere. And above the chromosphere, through the narrow transition region, the temperature rises even more steeply to the coronal temperatures of millions of Kelvin. This temperature inversion, The heating of the outer atmosphere to temperatures far above the photosphere cannot be explained by simple radiation from below. The photosphere is the hottest radiating surface, and radiation flows from hotter to cooler, so no purely radiative process can heat the chromosphere above the photospheric temperature. Something else must be depositing energy into the chromosphere and corona. And that something is, in all current understanding, related to the magnetic field. The magnetic field of a red dwarf threads the entire atmosphere from the deep convective interior to the outer corona. As the convective motions in the interior move the footpoints of magnetic field lines around on the photosphere, they do work on the field, injecting energy into it in the form of waves and currents propagating along the field lines into the upper atmosphere. This energy, deposited in the chromosphere and corona, heats these outer layers to their observed high temperatures through a combination of processes including the damping of magnetohydrodynamic waves, the dissipation of current sheets, and the reconnection of magnetic field lines. The chromosphere of a red dwarf is detectable in several ways. The most characteristic spectroscopic signature is emission in the hydrogen-Balmer lines, particularly the H-alpha line at 656 nanometers, which appears as a bright emission feature rather than the dark absorption line seen in cooler or less active stars. H-alpha emission from red dwarfs is a direct indicator of chromospheric heating and is widely used as a proxy for stellar activity. The fraction of red dwarfs showing H-alpha emission increases with decreasing mass and with younger age, reflecting the stronger magnetic activity of less massive and younger red dwarfs. In the most active red dwarfs, the H-alpha emission can be remarkably strong, indicating chromospheric temperatures and densities significantly above those of less active examples. Emission in ultraviolet lines of ionized metals, particularly magnesium and calcium, provides additional probes of the chromosphere. The calcium H and K lines at 396 and 393 nanometers, analogous to the same lines used to measure chromospheric activity in sun-like stars, are detectable in red dwarfs and vary with activity level and rotation rate. Ultraviolet observations from space-based telescopes, sensitive to the far ultraviolet emission from hot chromospheric and transition region plasma, have revealed the detailed temperature structure of the red dwarf outer atmosphere and shown that even apparently quiet red dwarfs maintain a persistently heated chromosphere at all times, not just during flares. Above the chromosphere, through the thin transition region where the temperature rises by a factor of 10 or more over a distance of only a few hundred kilometers, lies the corona, the outermost layer of the stellar atmosphere, a tenuous plasma of ionized gas at temperatures of 1 to 10 million Kelvin or more, extending millions of kilometers above the photosphere and merging gradually into the stellar wind that flows outward into space. The corona of the Sun is visible during total solar eclipses as the pearly white halo surrounding the darkened solar disk, a ghostly structure of streamers and loops and rays that extends far into space. Its million-degree temperature was established observationally in the 1940s through measurements of the ionization state of coronal ions, which require temperatures of millions of Kelvin to produce. The same puzzle that applies to the chromosphere applies to the corona in even more extreme form. How does the outermost atmospheric layer reach temperatures hundreds of times higher than the photospheric surface? The answer, as for the chromosphere, involves the dissipation of magnetic energy deposited from below, though the specific mechanisms of coronal heating remain an area of active research. The coronae of red dwarfs are, in many cases, more extreme than the Sun's. X-ray observations, which detect the thermal emission of coronal plasma at temperatures of millions of Kelvin, show that active red dwarfs are prodigiously luminous in X-rays relative to their total bolometric luminosity. The ratio of X-ray to bolometric luminosity for the most active red dwarfs approaches 1/10,000th, compared to roughly 1 millionth for the quiet Sun, meaning that active red dwarfs are pouring 10 to 100 times more energy per unit total luminosity into coronal heating than the quiescent Sun. Their coronae are hotter, denser, and more magnetically complex than the solar corona, sustained by the stronger magnetic fields and more vigorous convective driving of the red dwarf interior. The high coronal luminosity of active red dwarfs has important consequences for any planets orbiting them. The X-rays and extreme ultraviolet radiation from the corona, far more energetic than visible light, are absorbed in the upper atmospheres of planets and can drive photochemical reactions, dissociate molecules, and heat the upper atmosphere to the point where it expands and escapes to space. The atmospheric erosion driven by coronal X-ray and ultraviolet radiation from active young red dwarfs is one of the most significant challenges for planetary habitability in red dwarf systems, and the extent to which a planet can retain its atmosphere against this erosion depends critically on the strength of its magnetic field and the density of its atmosphere. Over billions of years, as the red dwarf ages and its rotation slows and its magnetic activity decreases, the coronal X-ray luminosity declines substantially. Old, slowly rotating red dwarfs have much quieter coronae than young, rapidly rotating ones, and their X-ray luminosity can be comparable to or even lower than the Sun's relative to total luminosity. The temporal evolution of coronal activity is therefore a crucial factor in assessing the long-term habitability of red dwarf planets. A planet that survives the vigorous early irradiation of a young active red dwarf may find itself in a much more benign environment once the star has aged into a quieter state. Beyond the corona, the stellar wind carries plasma outward from the red dwarf's atmosphere into the surrounding space. The stellar wind of the Sun, the solar wind, is a continuous outflow of charged particles, primarily protons and electrons, streaming outward from the corona at speeds of several hundred kilometers per second and filling the entire heliosphere with a tenuous but dynamically important plasma. The solar wind shapes the magnetospheres of the planets, erodes planetary atmospheres through sputtering and charge exchange, and eventually terminates at the heliopause where it meets the interstellar medium. The stellar winds of red dwarfs are difficult to measure directly, because the wind plasma itself emits very little radiation and the indirect proxies used to measure solar wind analogs are less well established for cooler stars. Nevertheless, several detection methods have been developed, including observations of the Lyman alpha absorption produced by neutral hydrogen at the interface between the stellar wind and the interstellar medium, and radio observations of the free emission from the ionized wind plasma. Current estimates suggest that red dwarf stellar winds have mass loss rates that vary enormously with activity level. Active, young red dwarfs may have winds with mass loss rates significantly higher than the Sun's current rate, driven by the stronger magnetic fields and more vigorous coronal heating of the active phase. Quiet, old red dwarfs may have winds comparable to or weaker than the Sun's. The detailed properties of red dwarf winds remain uncertain and are an active area of observational and theoretical investigation. The stellar wind of a red dwarf has important consequences for any orbiting planets. planets in the close-in habitable zones of red dwarfs, orbiting at distances of a few percent of an astronomical unit, are bathed in a stellar wind that is orders of magnitude denser than the solar wind at Earth's orbit, simply because the closer distance means encountering the wind before it has had as much volume to expand into. This dense stellar wind exerts ram pressure on planetary magnetospheres and can erode atmospheres through interactions with the ionosphere and upper atmosphere, potentially stripping lighter atmospheric constituents over long timescales. The interaction between the stellar wind and the planetary magnetic field produces a magnetosphere around the planet that can partially shield the atmospheric layers from direct wind interaction. Whether a planet in the habitable zone of a red dwarf can maintain a magnetic field strong enough for effective magnetospheric protection depends on its interior composition, its thermal state, and its rotation rate, all of which are affected by the tidal locking that red dwarf planets are expected to experience. The question of magnetospheric shielding in tidally locked red dwarf planets is one of the most actively discussed topics in the astrobiology of red dwarf systems. The coolest red dwarfs, those at the boundary between M and L spectral types, are cool enough that condensates, cloud-like formations of solid or liquid particles, can form in their atmospheres. At temperatures below approximately 2200 Kelvin, iron vapor begins to condense into iron droplets and eventually iron grains. Below approximately 2000 Kelvin, silicates condense into dust particles. Below approximately 1500 Kelvin, which puts us firmly in the L dwarf and T dwarf territory at the boundary with brown dwarfs, water clouds can form. These atmospheric condensates produce clouds in the most literal sense, regions of the atmosphere where the density of suspended particles is high enough to significantly affect the opacity, scattering and absorbing radiation in ways that change the emergent spectrum and the thermal structure of the atmosphere. Iron and silicate clouds in the atmospheres of the coolest M dwarfs and L dwarfs produce a reddening of the spectrum at near-infrared wavelengths and a filling in of some of the molecular absorption bands by the continuum opacity of the cloud particles. The cloud structures in the atmospheres of the coolest red dwarfs are not uniform layers but patchy, three-dimensional structures shaped by the atmospheric dynamics. Differences in cloud coverage between regions of the atmosphere produce photometric variability as the star rotates, with cloud-covered regions appearing darker and cloud-free regions appearing brighter. This cloud-induced variability has been detected in several late M and L dwarf systems and is one of the observational signatures of the complex atmospheric dynamics operating at the boundary between red dwarf and brown dwarf. For the warmer red dwarfs, above approximately 3000 Kelvin, the atmosphere is too hot for iron or silicate condensation, and the dominant opacity sources are the molecular gases, titanium oxide, vanadium oxide, water vapor, and other species that remain in the gas phase at these temperatures. The atmospheres of these stars are cloud-free in the condensate sense but are nevertheless complex, with strong molecular absorption features and a thermal structure shaped by the interaction of radiation, convection, and magnetic heating. The surface and atmosphere of a red dwarf are thus a layered system of extraordinary complexity, from the churning convective photosphere with its dark spot clusters and rising granules, through the heated chromosphere glowing in hydrogen and calcium emission, through the million-degree corona threaded with magnetic loops and arches, to the stellar wind streaming outward into the space between the stars. Each layer is shaped by the magnetic field generated in the convective interior below, and each layer has consequences for the environment experienced by any planet unlucky or lucky enough to orbit within the reach of this structured, magnetically active stellar atmosphere. From a distance, the red dwarf appears as a faint, dim, red point of light. Up close, it is anything but calm. On the 2nd of April, 1998, a red dwarf called EV Lacerti, a star of spectral type M3.5 located approximately 16 light-years from the Sun in the constellation Lacerta, released a flare. Not a modest flare. Not a routine burst of the kind that active red dwarfs produce dozens of times per day. A super flare. In the space of a few minutes, EV Lacerti released an amount of energy in X-rays and ultraviolet radiation alone that equaled 10,000 times the energy of the most powerful solar flare ever recorded. Its total flare energy, across all wavelengths, was estimated at roughly 10 to the 33 ergs, comparable to the entire energy output of the Sun over several hours, released from a star that under normal circumstances emits less than 1% of the Sun's total luminosity. The flare was so intense that it was detectable from Earth with relatively modest instruments, a brief, brilliant spike on the light curve of an otherwise unremarkable dim red point of light. EV Lacerti is not exceptional. It is one of many red dwarfs known to produce superflares regularly, in the class of flaring red dwarfs, collectively called flare stars or UV Ceti type stars after their prototype UV Ceti, includes hundreds of known examples in the solar neighborhood alone. Flaring is not a pathological behavior of a few unusual red dwarfs. It is a normal, expected, physically inevitable consequence of the strong magnetic fields and fully convective interiors of these stars, particularly when they are young and rapidly rotating. To understand the flares, we need to understand the magnetic field configurations that produce them. And to understand those configurations, we need to follow the magnetic field from the convective interior where it is generated, through the photosphere where it emerges, into the chromosphere and corona where it stores its energy, and finally to the moment of reconnection where that stored energy is catastrophically released. Magnetic field lines in a stellar atmosphere are not free to do whatever the local plasma motion dictates. In a highly conducting plasma, the magnetic field is frozen into the plasma, meaning that the field lines move with the plasma and the plasma moves with the field lines. This frozen-in condition, a consequence of the high electrical conductivity of hot ionized gas, means that when convective motions in the photosphere drag the footpoints of magnetic field lines around, the field lines are stretched, twisted, and braided by those motions, storing energy in the increasingly complex field configuration. Imagine a magnetic field loop anchored at both ends in the photosphere, arching through the corona above. The 2 footpoints of the loop are carried around by the convective granulation pattern beneath them, rotating around each other, drifting in opposite directions, pulled by the turbulent surface flows. Each displacement of a footpoint adds a small amount of energy to the field, twisting the loop slightly more, increasing the current that flows along it, building up the free magnetic energy stored in the non-potential component of the field configuration. Over hours and days, the accumulated energy in a sufficiently twisted and tangled coronal field can become enormous relative to the thermal and kinetic energy of the surrounding plasma. At some point, the configuration becomes unstable. The current sheet that forms between oppositely directed field regions becomes thin enough that the resistivity of the plasma, normally negligible in the highly conductive corona, becomes important in the thin sheet. The field lines on opposite sides of the current sheet, pointing in nearly antiparallel directions, begin to reconnect. The topology of the field changes, with field lines breaking and rejoining in a new, lower energy configuration. The energy stored in the stressed field is released suddenly, accelerating particles to high energies, heating the surrounding plasma to temperatures of tens of millions of Kelvin, driving plasma jets outward from the reconnection region at Alfvén speeds, and sending a pulse of radiation across the entire electromagnetic spectrum from gamma rays to radio waves. This is a stellar flare. Not an explosion in the sense of material being thrown off the star in large quantities, though coronal mass ejections can accompany flares. Not a nuclear event. Not a change in the star's basic structure. Just the sudden release of magnetic energy that has been building up in the coronal field configuration, stored there by the patient work of convective footpoint motions operating over hours and days and weeks before the reconnection event that releases it all at once. A typical moderate flare on an active red dwarf unfolds over a characteristic sequence of phases that mirrors the sequence of solar flares but is scaled to the more energetic conditions of the red dwarf corona. In the minutes before the flare, the coronal magnetic field in the flaring region has been building up stress for hours or days. The free energy in the configuration, the excess above the minimum energy potential field, may be 10 to 100 times the energy that will ultimately be released in the flare. The field is tightly wound, with strong current sheets threading through the corona above the active region. To an observer watching the chromospheric emission in H-alpha, the pre-flare phase may show subtle brightenings and small-scale dynamic events as the field continues to be stressed and small-scale reconnections begin at the margins of the unstable region. The impulsive phase begins when the primary reconnection event initiates. Within seconds to minutes, the magnetic energy stored in the reconnecting field region is converted into particle kinetic energy, thermal energy, and radiation with remarkable efficiency. Non-thermal electrons accelerated to energies of tens to hundreds of kilo-electron volts stream downward along the newly reconnected field lines toward the chromosphere, where they are stopped by the denser chromospheric gas, heating it explosively. The heated chromospheric plasma expands rapidly upward into the corona, filling the newly reconnected field loops with hot, dense plasma in a process called chromospheric evaporation. Simultaneously, the heated chromospheric footpoints radiate brilliantly in white light and in the ultraviolet, producing the sudden, dramatic brightening that makes large flares visible even in integrated light measurements. In the corona above the flare, the hot plasma filling the reconnected loops emits copiously in X-rays, producing the intense X-ray brightening that is one of the most reliable observational signatures of flares. The X-ray emission from a superflare on an active red dwarf can exceed the star's total quiescent X-ray luminosity by factors of 10 to 100. And the brightening at extreme ultraviolet wavelengths can be even more dramatic. Radio emission, produced by energetic electrons spiraling along magnetic field lines and by plasma waves excited in the flaring corona, accompanies many flares as a burst of coherent or incoherent radio radiation that can be detected across interstellar distances. The gradual phase follows the impulsive phase as the heated coronal plasma cools, radiating away its thermal energy over minutes to hours. The cooling plasma drains back down the field lines toward the chromosphere in coronal rain, and the magnetic field relaxes toward a new, lower energy equilibrium configuration. The flare emission fades across all wavelengths, returning the star to its quiescent state. For the largest superflares, the gradual phase can last hours, with the X-ray emission elevated above the quiescent level for many times longer than the brief, brilliant impulsive phase that is the flare's most dramatic moment. The largest flares on the most active red dwarfs, the superflares, are among the most energetic events that occur on stellar surfaces anywhere in the universe. Their energies, ranging from 10 to the 32 to 10 to the 36 ergs, dwarf the most powerful solar flares by factors of hundreds to millions. They release, in the space of minutes to hours, energies comparable to the total annual radiative output of the most luminous red dwarfs. They are, in terms of their energy release relative to the quiescent luminosity of their host star, the most extreme stellar surface events known. What conditions produce superflares? The key ingredients appear to be rapid rotation, strong magnetic fields, and the specific geometry of large-scale field configurations that can store particularly large amounts of free energy before reconnecting. Young red dwarfs rotating with periods of a few hours to a day have the strongest magnetic fields and the most frequent and energetic superflares. As a red dwarf ages and its rotation slows through magnetic braking, the flare rate and the maximum flare energy both decline, tracking the decline in magnetic activity with age. The flare frequency distribution of red dwarfs, the statistical relationship between flare energy and flare occurrence rate, follows a power law. Smaller flares are much more frequent than larger ones, with the number of flares per unit time scaling approximately as the flare energy raised to a negative power of about 1.5 to 2. This means that the cumulative energy deposited by all flares combined is dominated by the largest events, the superflares, while the occurrence rate in terms of number of events is dominated by the smallest detectable flares. Integrating over the full flare frequency distribution gives the total flare power, the energy per unit time delivered by all flares, which for the most active red dwarfs can be a significant fraction of the quiescent bolometric luminosity. The occurrence of superflares on red dwarfs is not confined to the youngest, most active examples. Even stars that appear relatively quiet in their quiescent emission can produce occasional superflares if they have a particularly favorable magnetic field configuration. The unpredictability of flares, their dependence on the instantaneous configuration of the coronal field rather than on time-averaged activity indicators, means that any active red dwarf is potentially capable of a superflare at any moment, without any detectable precursor in the quiescent emission. This unpredictability is one of the most challenging aspects of the red dwarf flare environment for any life forms that might inhabit red dwarf planets. Large solar flares are often accompanied by coronal mass ejections, massive eruptions of magnetized plasma from the solar corona that travel outward through the solar system at speeds of hundreds to thousands of kilometers per second. Coronal mass ejections carry billions of tons of plasma and magnetic field, and when they encounter the Earth's magnetosphere they can produce intense geomagnetic storms that disrupt satellite communications, power grids, and navigation systems. The most powerful historical geomagnetic storm, the Carrington event of 1859, was produced by a particularly energetic solar coronal mass ejection and is estimated to have been so intense that it would cause trillions of dollars of damage to modern technological infrastructure. If solar coronal mass ejections are destructive to technological civilization, what about the coronal mass ejections from active red dwarfs? The question is both physically fascinating and astrobiologically important, And the answer is complicated by the fact that stellar coronal mass ejections are extraordinarily difficult to detect directly at the distance of even the nearest stars. Indirect evidence for coronal mass ejections on red dwarfs comes from several sources. Blue-shifted absorption features and spectral lines formed in the chromosphere and transition region during flares suggest upward-moving plasma that could be interpreted as the early phase of a coronal mass ejection. Statistical arguments based on the observed solar relationship between flare energy and coronal mass ejection properties suggest that red dwarf superflares should be accompanied by coronal mass ejections of correspondingly enormous energy, carrying plasma masses of billions of tons moving at speeds of thousands of kilometers per second. However, there is a complication. Some theoretical models suggest that the strong magnetic fields of active red dwarfs may actually suppress the largest coronal mass ejections, because the overlying coronal field may be strong enough to confine the erupting plasma rather than allowing it to escape. In the Sun, the confining ability of the overlying field determines whether a given eruptive event produces a confined flare or a full coronal mass ejection. For stars with much stronger global magnetic fields than the Sun, the confinement threshold may be much higher, meaning that even very energetic eruptions may be magnetically trapped and unable to escape the stellar corona. The question of whether red dwarf superflares are accompanied by large coronal mass ejections or are instead largely confined events is one of the most important open questions in red dwarf stellar physics, with major implications for planetary habitability. For a planet orbiting in the habitable zone of a red dwarf, the flare environment presents a challenge that has no direct analog in the solar system. The habitable zone of a red dwarf is very close to the star, at orbital distances of roughly 0.02 to 0.3 astronomical units depending on the stellar luminosity, compared to Earth's orbital distance of 1 astronomical unit. A planet at this distance is much closer to the flaring star than Earth is to the Sun, and the radiation intensity it experiences scales as the inverse square of the distance. A planet at 0.1 astronomical units from its star experiences the same flare radiation 100 times more intensely than a planet at 1 astronomical unit. The most biologically damaging radiation from flares is the ultraviolet, particularly the far ultraviolet below 300 nanometers, which penetrates the upper atmosphere and can dissociate ozone molecules, destroy nucleic acids directly, and drive photochemical reactions that produce toxic compounds. For the most energetic superflares, the ultraviolet fluence at the surface of a habitable zone planet could be sufficient to sterilize any unprotected surface life and penetrate meters of water to damage aquatic organisms. Repeated superflares at the rate observed on the most active young red dwarfs could represent a significant barrier to the origin of life and the persistence of complex organisms. However, the situation is more nuanced than a simple calculation of UV flux might suggest. Whether the ultraviolet radiation from a flare reaches the planet's surface depends critically on the composition and thickness of the planet's atmosphere. A sufficiently thick atmosphere with adequate ozone concentration would absorb essentially all the biologically damaging UV radiation from even a very large flare before it reaches the surface. The question is not merely whether the flare is intense but whether the planet's atmosphere is an effective shield, and the answer depends on the planet's atmospheric mass, composition, and the photochemistry that links the flare UV to the ozone column. Simulations of the atmospheric response to red dwarf flares have produced a range of results depending on the assumed atmospheric composition and the flare spectrum. For Earth-like atmospheres with significant ozone columns, the surface UV increase during even moderate superflares may be survivable for most organisms. For atmospheres with reduced ozone, such as those that might result from a history of vigorous flare-driven ozone depletion or from the reduced UV environment of a quiet red dwarf that suppresses the photochemical production of ozone, the surface UV during a superflare could be dramatically higher. The interplay between flare activity, atmospheric chemistry, and surface habitability is a complex and incompletely understood system. For a planet orbiting in the habitable zone of a red dwarf, the flare environment presents a challenge that has no direct analog in the solar system. The habitable zone of a red dwarf is very close to the star, at orbital distances of roughly 0.02 to 0.3 astronomical units depending on the stellar luminosity, compared to Earth's orbital distance of 1 astronomical unit. A planet at this distance is much closer to the flaring star than Earth is to the Sun, and the radiation intensity it experiences scales as the inverse square of the distance. A planet at 0.1 astronomical units from its star experiences the same flare radiation 100 times more intensely than a planet at 1 astronomical unit. The most biologically damaging radiation from flares is the ultraviolet, particularly the far ultraviolet below 300 nanometers, which penetrates the upper atmosphere and can dissociate ozone molecules, destroy nucleic acids directly, and drive photochemical reactions that produce toxic compounds. For the most energetic superflares, the ultraviolet fluence at the surface of a habitable zone planet could be sufficient to sterilize any unprotected surface life and penetrate meters of water to damage aquatic organisms. Repeated superflares at the rate observed on the most active young red dwarfs could represent a significant barrier to the origin of life and the persistence of complex organisms. However, the situation is more nuanced than a simple calculation of UV flux might suggest. Whether the ultraviolet radiation from a flare reaches the planet's surface depends critically on the composition and thickness of the planet's atmosphere. A sufficiently thick atmosphere with adequate ozone concentration would absorb essentially all the biologically damaging UV radiation from even a very large flare before it reaches the surface. The question is not merely whether the flare is intense but whether the planet's atmosphere is an effective shield, and the answer depends on the planet's atmospheric mass, composition, and the photochemistry that links the flare UV to the ozone column. Simulations of the atmospheric response to red dwarf flares have produced a range of results depending on the assumed atmospheric composition and the flare spectrum. For Earth-like atmospheres with significant ozone columns, the surface UV increase during even moderate superflares may be survivable for most organisms. For atmospheres with reduced ozone, such as those that might result from a history of vigorous flare-driven ozone depletion or from the reduced UV environment of a quiet red dwarf that suppresses the photochemical production of ozone, the surface UV during a superflare could be dramatically higher. The interplay between flare activity, atmospheric chemistry, and surface habitability is a complex and incompletely understood system. The first planet ever confirmed to orbit in the habitable zone of a red dwarf was announced in 2016. It orbits Proxima Centauri, the nearest star to the Sun, at a distance of roughly 0.05 astronomical units, completing one orbit every 11.2 days. It has a minimum mass of approximately 1.3 Earth masses, making it likely a rocky world. It receives approximately 65% of the energy per unit area that the Earth receives from the Sun. And it is called Proxima Centauri b. The discovery generated enormous excitement in the scientific community and in the broader public, and rightly so. A potentially rocky, potentially temperate world orbiting the nearest star to the Sun, close enough in principle for a future spacecraft to reach on a timescale of decades at a significant fraction of the speed of light. The nearest possible inhabited world outside the solar system, orbiting a red dwarf that will still be burning 4 trillion years from now. Whether Proxima Centauri b is habitable is a question we cannot currently answer. Its mass is known only as a lower limit, leaving open the possibility that it is more massive and potentially gaseous. Its radius is unknown, so its density and interior composition are unconstrained. Its atmosphere, if it has one, has not been directly detected. Its surface, if it has one, has not been imaged. We know it exists and we know roughly where it orbits and we know approximately how much energy it receives. Everything else is inference and model. But its existence, and the existence of dozens of similar worlds discovered around other red dwarfs in the years since, tells us something profound about the universe's planetary inventory. Red dwarf planets are common. Extraordinarily common. And understanding why they are common, what kinds of worlds they are, and what their surfaces might be like requires tracing the planetary formation process in the specific physical environment of a red dwarf system from the protostellar disk all the way to the mature planetary system. The planets around a red dwarf form in the same fundamental way as planets around any star, from the solid and gaseous material in the protoplanetary disk that surrounds the young star during the first few million years of its existence. The disk is the reservoir from which planets accrete, the arena in which the competition between collisional growth, gravitational dynamics, and disk-planet interactions plays out over millions of years to produce the final planetary system architecture. But the protoplanetary disk around a red dwarf differs in important ways from the disk around a sun-like star, and those differences shape the planets that emerge from it. The most fundamental difference is the disk's mass. More massive disks produce more massive planets. The disk mass scales roughly with the stellar mass, so a red dwarf of 1/10 solar mass is expected to have a disk containing roughly 1/10 as much solid material as the disk around a sun-like star. This lower solid mass means less material available for building rocky planets, and the planets that form are expected to be systematically smaller and less massive than those forming in the more massive disks of sun-like stars. The temperature structure of the disk also differs systematically. The disk is heated primarily by the central star's radiation and by the viscous dissipation of the gas as it spirals inward. Around a red dwarf, the stellar luminosity is much lower, so the disk is colder at every radius than a disk at the same radius around a sun-like star. The snow line, the distance from the star inside which water ice sublimates and cannot condense, is correspondingly closer to the star. For a red dwarf of 1/10 solar mass, the snow line may be at only a few tenths of an astronomical unit, compared to roughly 2 to 3 astronomical units for the Sun. The innermost regions of the red dwarf disk, where the habitable zone planets will eventually form, are therefore located inward of or near the snow line, potentially in a region where water ice was available during planet formation. The availability of water ice at or near the habitable zone formation location is potentially significant for the water content of habitable zone planets. In the solar system, the Earth formed inward of the snow line and received its water primarily through delivery by water-rich asteroids and comets from the outer solar system after its initial formation. In a red dwarf system, habitable zone planets may have formed in a region where water ice was locally abundant, potentially giving them more generous initial water endowments than the Earth received. The detailed water budget of red dwarf habitable zone planets depends on the disk temperature structure, the efficiency of radial mixing and drift, and the dynamical history of the forming planetary system, all of which vary from system to system. Of all the physical differences between red dwarf planets and solar system planets, none is more consequential for the character of the planetary environment than tidal locking. Tidal locking is the process by which the gravitational tidal forces exerted by a massive body on an orbiting body slow the orbiting body's rotation until its rotation period equals its orbital period, so that the same face always points toward the central body. The Moon is tidally locked to the Earth in this way, always showing us the same near side. In the outer solar system, many of the moons of the giant planets are tidally locked to their parent planets. For planets orbiting in the habitable zones of red dwarfs, tidal locking to the host star is expected to be essentially inevitable on timescales short compared to the stellar lifetime. The habitable zone is so close to the star, at orbital distances of 0.02 to 0.3 astronomical units, that the tidal forces are many orders of magnitude stronger than those experienced by Earth from the Sun. The timescale for tidal locking scales as the orbital distance raised to the sixth power divided by the stellar mass raised to the second power, and for typical red dwarf habitable zone parameters this timescale is between a few million and a few billion years, short compared to the multi-trillion-year main sequence lifetime of the star. Any planet that has been in the red dwarf habitable zone for more than a few billion years is almost certainly tidally locked. A tidally locked planet is a world of permanent extremes. The hemisphere permanently facing the star, the day side, is illuminated and heated continuously for the entire planetary lifetime. The hemisphere permanently facing away, the night side, is in eternal darkness, never receiving direct stellar radiation. The subsolar point, the spot on the day side directly beneath the star at noon, receives the maximum stellar flux and is the hottest region of the planet. The anti-solar point on the night side is the coldest, potentially cold enough for any atmospheric gases to freeze out and precipitate as snow if the atmosphere is too thin to efficiently redistribute heat. The atmospheric response to tidal locking is one of the most studied topics in the atmospheric science of red dwarf planets. The key question is whether the atmosphere can transport heat efficiently enough from the permanent day side to the permanent night side to prevent the night side from becoming a cold trap where atmospheric gases freeze out, a process called atmospheric collapse. If the atmosphere collapses, the planet becomes effectively airless on the night side and uninhabitable everywhere. If the atmosphere survives, the global climate depends critically on the efficiency of the atmospheric heat transport and the resulting temperature distribution across the planetary surface. Modern three-dimensional climate models of tidally locked planets have produced a more optimistic picture than early simplified estimates suggested. For planets with Earth-like atmospheric masses and compositions, the atmosphere is generally capable of redistributing heat from the day side to the night side efficiently enough to prevent collapse, even for the most slowly rotating tidally locked states. The night side remains colder than the day side, but the temperature difference may be only a few tens to 100 Kelvin rather than the hundreds of Kelvin that would cause atmospheric gases to freeze. The day side is warmer than a comparable non-locked planet would be, but not necessarily dramatically so. The climate of a tidally locked planet with a substantial atmosphere is extreme by Earth standards but not necessarily incompatible with liquid water over some portion of the surface. The atmospheric circulation on a tidally locked planet is fundamentally different from that on a rapidly rotating planet like the Earth. On Earth, the Coriolis effect, produced by the planet's rotation, organizes the atmospheric circulation into the familiar pattern of trade winds, jet streams, and mid-latitude weather systems that distribute heat and moisture around the globe. On a tidally locked planet, the rotation is so slow, completing once per orbit, that the Coriolis effect is weak and the atmospheric circulation is instead driven primarily by the day-night temperature contrast. The dominant circulation pattern on a tidally locked planet with a dense atmosphere is called the thermally direct circulation. Air heated on the day side rises in a broad column above the subsolar point, spreads outward at high altitude toward the night side, cools as it flows away from the heat source, sinks over the night side, and returns near the surface toward the subsolar point in the low-altitude return flow. This circulation pattern, a day-to-night overturning driven by the permanent temperature contrast, carries heat from the day side to the night side far more efficiently than simple radiative cooling would allow. Superimposed on this large-scale overturning circulation are jet streams and eddies produced by the interaction of the circulation with the planet's rotation and with topography. General circulation models consistently predict the presence of a superrotating equatorial jet stream on tidally locked planets, a band of fast eastward flowing air at low latitudes that carries heat from the day side to the night side and introduces an asymmetry between the morning and evening sides of the planet. This superrotation has been tentatively detected in observations of hot Jupiter exoplanets, which are also tidally locked and whose atmospheric circulation is expected to be analogous to that of tidally locked rocky planets but at much higher temperatures. The terminator, the great circle dividing the permanent day side from the permanent night side, is one of the most distinctive features of the tidally locked planet's geography. Along the terminator, the star hangs perpetually on the horizon, never rising and never setting, casting a permanent oblique illumination that produces a narrow habitable band of intermediate temperatures between the potentially scorched day side and the potentially frozen night side. If liquid water exists anywhere on the surface of a tidally locked planet, the terminator region is one of the most probable locations, caught between the extremes, receiving enough stellar energy to melt ice without receiving so much that water boils away. The sky above the terminator region of a tidally locked planet in a red dwarf system would be one of the most alien and most beautiful in the imaginable universe. The star hangs at the horizon, enormous and red, never moving, always in the same position relative to the landscape. On one side, the bright crescent of the day side stretches away, lit by the permanent red-tinged sunlight. On the other, the dark hemisphere fades into a starfield undisturbed by any rising or setting sun. The terminator itself is a region of permanent dawn and dusk, the sky a deep, burning orange where the star meets the horizon and a velvet black overhead. The weather along the terminator, driven by the convergence of warm dayside air and cold nightside air, might be permanently stormy, a band of clouds and rain and wind that circles the planet like a permanent atmospheric front. In February 2017, the announcement of the TRAPPIST-1 system sent a wave of excitement through the astronomical community that has not fully subsided in the years since. TRAPPIST-1 is a small, dim, ultra-cool red dwarf approximately 40 light-years from the Sun in the constellation Aquarius. It has a mass of approximately 8% of the solar mass, placing it near the hydrogen-burning minimum and making it one of the least massive true stars known. And it hosts 7 confirmed planets, all of them roughly Earth-sized, 3 of them potentially in the habitable zone. The 7 TRAPPIST-1 planets, designated TRAPPIST-1b through TRAPPIST-1h in order of increasing orbital distance, orbit at distances ranging from approximately 0.011 to 0.063 astronomical units, all closer to their star than Mercury is to the Sun. Their orbital periods range from 1.5 days for the innermost to 19 days for the outermost. Their masses range from roughly 0.3 to 1.4 Earth masses. Their densities, measured from the combination of transit radii and radial velocity or transit timing variation masses, span a range that includes compositions from iron-rich and rocky to water-rich and possibly ice-covered. The 3 planets in or near the habitable zone, TRAPPIST-1e, F, and G, are among the most studied exoplanets in history. TRAPPIST-1e, with a mass of approximately 0.77 Earth masses and a radius of approximately 0.92 Earth radii, receives approximately 66% of the energy per unit area that Earth receives from the Sun, placing it in the inner habitable zone. Its density, approximately the same as the Earth's, is consistent with a rocky composition. If it has an Earth-like atmosphere, it could potentially support liquid water on its surface. It is, by current assessment, one of the most Earth-like planets known outside the solar system. The TRAPPIST-1 system has been observed by the James Webb Space Telescope, which has the sensitivity and spectroscopic capability to begin characterizing the atmospheres of these planets through transmission spectroscopy. Early results from JWST observations of TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets, have provided important constraints on the absence of thick secondary atmospheres on these worlds, suggesting that the innermost planets may have been stripped of their atmospheres by the early flare activity of the young TRAPPIST-1 star. The results for the outer, potentially habitable planets remain an active area of ongoing observations that will continue to refine our understanding of this extraordinary system. The TRAPPIST-1 system is the best current laboratory for understanding the properties and potential habitability of red dwarf planets. Its compact architecture, with 7 roughly Earth-sized planets in a small orbital volume, its proximity at 40 light-years, and its favorable geometry for transit observations have made it the most intensively studied exoplanetary system in history. Whatever we learn about TRAPPIST-1, we learn about red dwarf planet formation, red dwarf planetary atmospheres, and red dwarf habitability more broadly, because TRAPPIST-1 is in many ways a typical ultra-cool red dwarf, and its planetary system is expected to be broadly representative of this stellar class. The TRAPPIST-1 system and Proxima Centauri b represent only a fraction of the planetary diversity expected around red dwarfs. Planet formation in red dwarf systems produces a range of planetary types spanning from sub-Earth mass rocky bodies to super-Earths with thick gaseous envelopes, and from dry, rocky worlds to water worlds with global oceans hundreds of kilometers deep. Super-Earths and mini-Neptunes, planets with masses between roughly 2 and 10 Earth masses, are among the most common planet types detected around red dwarfs. These intermediate mass objects occupy the mass range between the clearly rocky planets and the clearly gaseous giant planets, and their compositions span a wide range. Some are rocky, with silicate and iron compositions similar to Earth but scaled to larger sizes. Others are water worlds, with large fractions of their mass in the form of water ice or liquid water. Still others have retained significant amounts of hydrogen and helium, accumulated from the protoplanetary disk gas during formation, giving them extended gaseous envelopes that make them more like scaled-down versions of Uranus and Neptune than like rocky planets. The distinction between rocky super-Earths and water worlds is of profound astrobiological significance. A water world with a global ocean hundreds of kilometers deep would be covered by high-pressure ice phases at its base, isolating the rocky seafloor from the ocean above and potentially preventing the geochemical cycling between rocks and ocean water that many theories of life's origin require. The carbonate-silicate cycle, which regulates the Earth's long-term climate through the geological exchange of carbon between the atmosphere and the mantle, requires subduction of carbonate rocks into the mantle and volcanic outgassing of carbon dioxide, processes that may operate differently or not at all on a water world. The habitability of water worlds is an open question that involves not just the presence of liquid water but the geochemical conditions that liquid water alone cannot guarantee. At the other extreme, some red dwarf habitable zone planets may be essentially dry, having formed in disk regions poor in water ice and having received little late-stage water delivery. A dry rocky planet with an arid surface and limited hydrological cycling might support life in restricted surface environments, particularly at the terminator region where temperatures are moderate and any water that does exist might be concentrated in a narrow habitable band. The range of water contents possible in red dwarf habitable zone planets spans orders of magnitude, from bone-dry to ocean worlds, and the actual water content of any given planet depends on its formation history and dynamical evolution in ways that vary enormously from system to system. Imagine standing on the surface of a rocky, tidally locked planet in the habitable zone of a red dwarf. The planet is old enough that its star has settled into the quiet phase of its main sequence evolution, its flare rate reduced to manageable levels, its coronal radiation diminished from the vigorous early phase. The atmosphere is breathable, let us say, an assumption we make not because it is guaranteed but because it allows us to complete the thought experiment. The star hangs in the sky, and it is not the sun. It is larger in angular size than the sun appears from Earth, perhaps 3 to 5 times the apparent diameter, because the planet is so much closer to it. But it is far dimmer in surface brightness, its ruddy light carrying less energy per unit area than the sun's yellow-white glare. It does not hurt to look at directly, at least not the way the sun does, its light more like a very bright full moon than a blinding noon sun. The color of its light is a deep orange red, the color of a fire seen from across a field, and everything it illuminates takes on that tint. Rocks, soil, clouds, the surface of any body of water, all touched with the color of embers. The sky itself, if the planet has a nitrogen-oxygen atmosphere similar to Earth's, would appear a different color from Earth's blue sky. The blue color of Earth's sky results from Rayleigh scattering, the preferential scattering of short-wavelength blue light by atmospheric molecules. In a red dwarf system, the incoming light is dominated by red and infrared wavelengths, with far less blue and ultraviolet than sunlight contains. The Rayleigh scattering of this redder light would produce a sky that is not blue but a dim, muted tone, perhaps orange-yellow at the brightest times, fading through dusty oranges and purples away from the star. At night, on the dayside hemisphere there is no night, but from the terminator region or from the night side, if there is any habitable territory there, the stars would be spectacular. No moon cycles the planet's sky, because tidally locked planets do not typically have large moons on stable orbits. No aurora paints the polar sky in the colors of solar particles, though there might be auroral activity driven by the stellar wind interaction with the planetary magnetic field. Just the stars, and the Milky Way, and the knowledge that the star will never rise or set but is always waiting on the other side of the terminator, always exactly where it was when you last looked. It is an alien world. Profoundly, thoroughly alien in its rhythms, in its light, in its weather, in its sky. And yet it orbits a star that is in every physically essential way like 10 to the 23rd other stars in the observable universe, the most common kind of star there is, the default star of a universe that prefers patience over brilliance. Whether anything looks up at that sky and wonders about the universe is the question we turn to next. Life on Earth has existed for approximately 4 billion years. From the first self-replicating molecules in the Hadean oceans to the first bacteria to the first multicellular organisms to the first animals to the first vertebrates to the first land plants to the first mammals to the first primates to the first humans capable of asking the question of whether they are alone in the universe, 4 billion years of continuous biological history have unfolded on a single rocky planet orbiting a single ordinary yellow star. 4 billion years is, by any human measure, an incomprehensibly long time. And yet it is less than half the Sun's total main sequence lifetime. The Sun has 5 billion years remaining. When those 5 billion years are spent and the Sun swells into a red giant, life on Earth will almost certainly have ended long before, as the Sun's gradually increasing luminosity renders the surface too hot for liquid water perhaps a billion years from now. The window of solar habitability for Earth, 10 billion years in total from the Sun's birth to the point where it becomes too luminous, is finite, definite, and already more than half expired. Now consider a planet in the habitable zone of a red dwarf with 1/10 the mass of the Sun. Its star will burn for approximately 10 trillion years. 10,000 billion years. If life emerges on that planet at the same point in the stellar lifetime that life emerged on Earth, which is to say within the first billion years, it will have a habitable window of roughly 10 trillion years to develop, evolve, complexify, and explore the universe. That is 2,500 times longer than the habitable window available to life on Earth. What could life do with 2,500 times more time than Earth life has had? What might evolution produce? What might intelligence accomplish? What might civilizations build and discover and become? Over 10 trillion years of continuous habitable conditions on a world lit by a dim, patient, permanent red star. We do not know. We have only one example of life, and it has had only 4 billion years. But the question, considered seriously, is one of the most profound in all of science. And answering it requires first asking whether red dwarf planets can host life at all, which in turn requires working through all the challenges and all the advantages that the red dwarf environment presents to the emergence and persistence of living systems. The case against habitability around red dwarfs is substantial and has been made seriously by serious scientists. It rests on several distinct lines of argument, each pointing to a different aspect of the red dwarf environment that differs from the solar environment in ways potentially hostile to life. The first and perhaps most fundamental challenge is the pre-main sequence luminosity problem discussed in an earlier chapter. Before a red dwarf settles onto the main sequence, it passes through a prolonged pre-main sequence contraction phase during which its luminosity is significantly higher than its eventual main sequence value. For a red dwarf of 1/10 solar mass, this pre-main sequence phase lasts approximately 1 billion years, during which the luminosity is high enough to place the eventual main sequence habitable zone within the runaway greenhouse threshold. Any planet that will eventually reside in the habitable zone spends the first billion years of its existence receiving too much energy, potentially evaporating its water inventory and losing hydrogen to space through the rapid escape driven by the high ultraviolet luminosity of the young, active star. Whether this pre-main sequence desiccation is irreversible depends on the detailed physics of atmospheric escape, the planet's initial water inventory, and the rate at which hydrogen escape fractionates oxygen relative to hydrogen. If the planet begins with a very large water inventory, enough that even after a billion years of hydrogen escape some water remains, the planet might survive the pre-main sequence phase with a habitable ocean intact. If the planet begins with a water inventory similar to Earth's, the early escape may be sufficient to leave it essentially dry. The outcome is sensitive to initial conditions that vary from planet to planet and that cannot currently be determined for any specific system. The second major challenge is the flare environment, which we explored in the previous chapter. Young, active red dwarfs produce superflares at rates that would bathe any habitable zone planet in extreme ultraviolet and X-ray radiation far more intense than the Earth receives from the Sun. This radiation can drive atmospheric escape, photodissociate molecules in the upper atmosphere including ozone, and deliver potentially sterilizing ultraviolet doses to any surface life. Whether an Earth-like atmosphere can survive and protect life through this early active phase is uncertain and depends on the balance between radiation-driven escape and volcanic replenishment of the atmosphere. The third challenge is tidal locking. As we discussed, habitable zone planets around red dwarfs are expected to be tidally locked, presenting a permanent day side and a permanent night side to their star. The climate consequences of tidal locking are complex and not necessarily fatal to habitability, as modern climate models suggest, but they are profound. The absence of a day-night cycle eliminates one of the fundamental temporal rhythms that shapes biology on Earth. The permanent illumination of the day side and permanent darkness of the night side create extreme environmental gradients that may constrain any life to narrow habitable zones along the terminator. The large-scale atmospheric circulation patterns of tidally locked planets, while probably adequate to prevent atmospheric collapse, may produce extreme weather patterns and persistent storm systems at the terminator that challenge the persistence of surface life. A fourth challenge is the potential depletion of ultraviolet light in the habitable environment of an old, quiet red dwarf. This may seem counterintuitive. Is not the absence of dangerous ultraviolet radiation a good thing? For life as it already exists, yes. But for the origin of life, ultraviolet light may be necessary. Several of the most promising abiogenesis pathways, the chemical routes by which non-living chemistry might give rise to the first self-replicating molecules, require ultraviolet photons to drive the key bond-breaking and bond-forming reactions. In particular, The cyanosulfidic chemistry proposed by the chemist John Sutherland as a plausible route to the simultaneous emergence of nucleotides, amino acids, and lipid precursors requires ultraviolet light in the 200 to 280 nanometer range to drive critical steps. A red dwarf produces very little radiation at these wavelengths even during its active phase and almost none during its quiet main sequence. If ultraviolet light is necessary for abiogenesis, red dwarf habitable zone planets may be stuck at the prebiotic chemistry stage, unable to take the photochemical steps that initiate life. The case for red dwarf habitability is equally serious and has been made with increasing conviction as our understanding of both red dwarf environments and the robustness of life has deepened. It rests on a different set of arguments, each pointing to ways in which the red dwarf environment may actually favor the emergence and persistence of life rather than preventing it. The most powerful argument for red dwarf habitability is the sheer number of red dwarf planets and the length of the habitable window. There are approximately 75 billion red dwarf stars in the Milky Way alone, each expected to host multiple rocky planets, and each rocky planet in the habitable zone has a potential window of trillions of years. Even if the probability of life emerging on any given red dwarf habitable zone planet in any given billion-year period is 1,000 times lower than the probability on an Earth-like planet around a Sun-like star, the combination of vastly more planets and vastly longer habitable windows means that the expected total number of life-bearing red dwarf planets in the galaxy could still exceed the number of life-bearing Sun-like star planets by an enormous margin. Numbers and time are powerful arguments, and both favor red dwarfs. The second argument concerns the stability of the habitable environment once the red dwarf has settled into its quiet main sequence phase. A quiet old red dwarf changes almost imperceptibly over billions of years. Its luminosity is nearly constant. Its flare rate is low. Its coronal radiation is modest. It does not brighten significantly the way the Sun does over its main sequence lifetime, a brightening that will eventually push the Earth out of the habitable zone. The habitable zone of a quiet red dwarf is stable over timescales that are geological in the sense of being effectively permanent. For life that has survived the early challenges, the subsequent environment is one of extraordinary stability, offering time for evolution to explore possibilities that the shorter solar main sequence would never permit. The third argument addresses the ultraviolet problem directly. While red dwarfs produce little ultraviolet radiation in their quiescent phase, their flares do produce significant ultraviolet bursts. Several research groups have argued that the ultraviolet from red dwarf flares, though episodic rather than continuous, might be sufficient to drive the photochemical reactions required for prebiotic chemistry. A pattern of intermittent ultraviolet exposure separated by long periods of quiescent darkness might actually be favorable for certain abiogenesis pathways, particularly those that require both UV-driven synthesis steps and UV-free periods for the products to accumulate and react further. The flare-driven ultraviolet environment of a young red dwarf might be not an obstacle to life but a driver of it. The fourth argument concerns the photosynthesis question. Red dwarf light is predominantly red and near-infrared, with very little blue and ultraviolet. Earth's photosynthesis uses chlorophyll molecules that absorb primarily in the red and blue parts of the visible spectrum, but this is not a fundamental constraint on photosynthesis in general. The quantum efficiency of photosynthesis, the fraction of absorbed photons that drive useful chemistry, depends on the wavelength of the absorbed photons. Longer wavelength photons carry less energy per photon, but a photosystem engineered by evolution to use multiple lower energy photons in a cascade could potentially achieve the same thermodynamic work as a system using fewer higher energy photons. Theoretical analyses of photosynthesis under red dwarf light have suggested that adapted photosystems could function with reasonable efficiency, and some researchers have proposed that life on a red dwarf planet might evolve photosystems that appear black to our eyes, absorbing essentially all the available light across the red and near-infrared spectrum to maximize energy capture from the dim stellar source. On Earth, liquid water is the universal solvent and medium of biochemistry. Every known living organism requires liquid water to function, and the search for life in the universe is, in large part, a search for environments where liquid water is stable on planetary surfaces or in subsurface reservoirs. The habitable zone is defined by the range of orbital distances at which a planet with an appropriate atmosphere can maintain liquid water on its surface, and the entire framework of habitability assessment rests on this water-centered definition. For a tidally locked planet around a red dwarf, the distribution of liquid water is more complex than for a rapidly rotating planet like the Earth. The permanent day side may be warm enough for liquid water over a wide area, potentially hosting shallow seas or a deep global ocean under the permanent illumination of the red star. The night side may be cold enough for water ice, covered by a permanent ice sheet supplied by atmospheric water vapor that freezes out as it is transported from the warm day side to the cold night side. The terminator region, between the two extremes, may host a band of intermediate temperatures where liquid water coexists with ice in seasonal free but geographically diverse conditions. The subsurface ocean is another possibility that deserves attention. On Earth, the deep subsurface hosts an enormous biomass of microbial life sustained not by photosynthesis but by the chemical energy released by reactions between water and rock, particularly the serpentinization of olivine-rich mantle rocks by water, which releases hydrogen that chemolithotrophic bacteria can use as an energy source. This deep subsurface biosphere, if it exists, is completely independent of sunlight and would be equally viable on a tidally locked planet, on a planet too cold for surface liquid water, or even on a planet whose surface has been rendered uninhabitable by flare radiation. If life can survive in the deep subsurface of a red dwarf planet as it survives in the deep subsurface of Earth, the surface radiation environment becomes less of a barrier. The possibility of subsurface liquid water oceans maintained by tidal heating adds another dimension. In the outer solar system, the moons Europa, Enceladus, Titan, and Ganymede all maintain subsurface liquid water oceans sustained by tidal heating from the gravitational interaction with their parent planets. A similar process could operate on moons of gas giant planets in red dwarf systems, or even on the rocky planets themselves if they are caught in resonant orbital configurations that maintain ongoing tidal dissipation. A world that is too cold on its surface for liquid water but too warm in its interior to freeze completely, maintained in this intermediate state by tidal heating from its star, could host subsurface oceans accessible to life forms that never need to see the red sky above. Perhaps the most profound argument for red dwarf life is also the most speculative, the argument from timescale. Life on Earth has had 4 billion years to produce everything from bacteria to blue whales, from the first photosynthesis to the first agriculture, from the first nervous system to the first radio telescope. What might evolution produce given not 4 billion years but 4 trillion? The question is genuinely difficult to answer because we have only one example of the evolutionary process and it covers only one range of timescales. We know that evolution is cumulative. Each generation builds on the adaptations of the previous ones, and the longer the process continues, the larger the space of possible adaptations that has been explored. We know that intelligence and complex behavior have evolved independently multiple times on Earth, invertebrates, encephalopod mollusks, and some arthropods, suggesting that the evolution of at least rudimentary intelligence is not a vanishingly improbable event given sufficient time and selective pressure. We know that technology-capable intelligence has emerged at least once in the several 100 million years since the Cambrian explosion. If intelligence and technology can emerge in a few 100 million years of animal evolution, and if animal-equivalent complexity can evolve from microbial life in roughly 3 billion years, then a red dwarf planet with 10 trillion years of habitable conditions has the potential to cycle through the entire process of evolution from first life to intelligence not once but many times over, with thousands of opportunities to restart if extinction events periodically reset the evolutionary clock. The sheer depth of evolutionary time available on a red dwarf planet is staggering in its implications. A civilization that emerged on a red dwarf planet 2 trillion years from now, in a universe where all the sun-like stars have exhausted their hydrogen and the stellar sky is dominated by cooling white dwarfs and the remaining red dwarfs, would look out at a universe nearly empty of the bright lights that illuminate our current sky and wonder whether they are alone in a darkening cosmos. And they might, if they had sufficiently long-range instruments and sufficiently patient scientific traditions, detect the faint traces of the radio transmissions and chemical biosignatures of civilizations that rose and fell billions of years before them on other red dwarf worlds, a palimpsest of life stretching back across trillions of years of cosmic history. Whether any of this happens depends on whether the initial step, the emergence of life from non-living chemistry on a red dwarf habitable zone planet, is possible at all. We do not yet know the answer. We have one data point, our own biosphere, and it is not on a red dwarf planet. The extension of our single data point to the red dwarf environment requires theoretical extrapolation that is scientifically principled but not yet observationally tested. If life does exist on red dwarf planets, how would we detect it? The answer lies in the concept of a biosignature, a chemical, physical, or electromagnetic signal that is produced by biological processes and that would not be present, or would be present only at much lower levels, in the absence of life. The most discussed biosignatures for rocky exoplanets are atmospheric gases that are produced by biological metabolism and that would quickly be destroyed by chemical reactions in the absence of continuous biological replenishment. Oxygen is the biosignature most associated with life on Earth. The oxygen in Earth's atmosphere, approximately 21% by volume, is maintained entirely by photosynthesis. In the absence of photosynthetic life, the oxygen would react with reduced volcanic gases and with surface rocks and be consumed within a few million years. The detection of oxygen in the atmosphere of an exoplanet would therefore be strong, though not conclusive, evidence for photosynthetic life. The combination of oxygen with methane would be even more compelling, because oxygen and methane react rapidly with each other and cannot coexist at significant concentrations without continuous replenishment from both an oxygen-producing and a methane-producing biosphere. For red dwarf planets specifically, the detection of biosignatures through transmission spectroscopy with telescopes like the James Webb Space Telescope is challenging but potentially achievable for the nearest and most favorable systems. TRAPPIST-1, at 40 light-years, is the best current target. Its planets transit their star regularly, and each transit provides an opportunity to observe the starlight filtered through the planetary atmosphere and measure the absorption of atmospheric gases at specific wavelengths. The detection of oxygen or ozone in the spectrum of a TRAPPIST-1 habitable zone planet would be one of the most significant scientific discoveries in human history. The interpretation of biosignatures in red dwarf systems requires particular care because some abiotic processes can mimic biological signals. Oxygen can be produced by the photolysis of carbon dioxide and water vapor by ultraviolet light, without any biology involved. On a planet that has lost its hydrogen through escape while retaining the oxygen left behind, an oxygen-rich atmosphere might be entirely abiotic in origin. Distinguishing biotic from abiotic oxygen requires additional context, including the simultaneous detection of other atmospheric species, the measurement of isotopic ratios, and the assessment of the planet's bulk composition and interior state. The search for life on red dwarf planets is not a distant future project. It is happening now, with current telescopes providing the first tentative atmospheric constraints on the TRAPPIST-1 planets, and with the next generation of extremely large ground-based telescopes and potential future space missions expected to push the characterization of red dwarf habitable zone atmospheres to the level where biosignature detection becomes plausible. The answer, when it comes, will be the most important answer in the history of science. And it will be an answer about red dwarf planets, because red dwarfs are the most common stars, their habitable zone planets the most numerous potentially habitable worlds, and their close proximity and favorable transit geometries the most accessible targets for the kind of atmospheric characterization that biosignature detection requires. The smallest stars may hold the biggest answer. There is something philosophically appropriate about the possibility that life, if it is widespread in the universe, may predominantly reside on the planets of red dwarf stars. Something that resonates with what we have learned about the red dwarfs themselves over the course of this journey. Red dwarfs are patient. They do not rush. They do not blaze briefly and spectacularly and then collapse. They burn their fuel with an extraordinary conservation, a refusal of excess, a commitment to the long game that is without parallel in the stellar population. They have been burning since the universe was young, and they will still be burning when every other star has gone dark. They are the survivors, the last fires, the stars that outlast everything else. If life on red dwarf planets is possible, then life, too, is patient. Emerging on worlds that orbit patient stars, evolving over timescales that dwarf the current age of the universe, adapting to a light that is dim and red and permanent and never changing. Life that has never seen a sunrise or a sunset. Life that has never experienced a season. Life that has known only the eternal red glow of a star that is in no hurry, ever, to stop shining. Perhaps that patience is instructive. Perhaps the universe, in producing so many red dwarfs and surrounding them with so many potentially habitable worlds, is offering a particular lesson about time and patience in the long game that complex systems play when they are given the opportunity. Not a lesson we can apply directly, given our sun's 5 billion year remaining lifetime and our own far shorter lives. but a lesson in perspective, available to anyone willing to contemplate the full span of cosmic time and ask what might be doing so in the dim, patient light of the most common stars. The red dwarfs are waiting. They have been waiting for the universe to produce life on their worlds since the first of them ignited in the early universe. They will continue waiting, burning their patient fires, for trillions of years more. Whether anything waits with them, alive and wondering, is the question that the next generation of telescopes may finally begin to answer. Tonight, the question is enough. The waiting is enough. The patient red light, falling on worlds we cannot yet see clearly, is enough. Rest now, in the dim glow of that light. The sun is aging. You cannot see it happening, because the process is too slow for any human lifetime to register, but it is happening continuously, at every moment, as the hydrogen in the solar core is consumed and replaced by helium, as the mean molecular weight of the core gradually rises, as the core contracts fractionally and heats fractionally and the fusion rate adjusts and the luminosity nudges upward. Over the 4.5 billion years since the sun ignited, its luminosity has increased by approximately 30%. Over the next 5 billion years, it will increase by roughly another 30%, enough to push the Earth permanently out of the habitable zone before the sun even begins its red giant expansion. The sun is aging steadily, visibly on geological timescales, irreversibly toward a future that is very different from its present. A red dwarf ages differently. In a fully convective red dwarf, the changes that aging produces in the sun, the accumulation of helium in the core, the stratification of composition between core and envelope, the gradual mean molecular weight increase that drives luminosity evolution, are either suppressed or dramatically slowed by the convective mixing that continuously homogenizes the stellar interior. The red dwarf ages, but it ages with a patience that makes the sun's evolution look hurried. To follow the aging of a red dwarf properly, we need to track several things simultaneously: the composition of the stellar interior as hydrogen is consumed and helium accumulates, the thermal structure of the star as its energy-generating properties slowly change, the external appearance of the star as its luminosity and temperature respond to the interior evolution, and the magnetic behavior of the star as its rotation rate changes over billions and trillions of years. Each of these threads of evolution tells a different part of the story, and together they paint a portrait of aging that is unlike anything else in the stellar zoo. Every nuclear reaction in the core of a red dwarf produces helium as its end product. The proton-proton chain converts 4 hydrogen nuclei into one helium-4 nucleus. The helium-4 that accumulates is the ash of nuclear burning, the product of the energy release that powers the star, and it cannot itself be burned at the temperatures available in a red dwarf core. In the sun, this helium ash accumulates in the core and is not mixed away. It sits there, stratified, enriching the core in helium and depleting it in hydrogen, creating a composition gradient that progressively changes the mean molecular weight of the core material and drives the structural adjustments that cause the sun to slowly brighten and expand over its main sequence lifetime. In a fully convective red dwarf, the helium ash does not stay where it falls. The convective circulation picks it up and carries it outward through the star, distributing it throughout the entire convective volume. The helium produced in the core today will be spread throughout the star on a timescale of years to decades by the convective overturning. The star therefore evolves not as a two-component system with a helium-rich core and a hydrogen-rich envelope, but as a single, well-mixed system in which the overall helium fraction increases gradually and uniformly as hydrogen is consumed. This uniform helium enrichment drives the red dwarf's aging in a way that is qualitatively different from the Sun's evolution. Because the entire star's composition changes together rather than just the cores, the structural response is more gradual and more uniform. The result is a slow, steady, nearly linear brightening of the red dwarf over its main sequence lifetime, with the luminosity increasing modestly and continuously rather than accelerating the way the Sun's does when its helium core grows. The total luminosity increase over the entire main sequence lifetime of a fully convective red dwarf is estimated at approximately 20 to 40%, comparable in fractional terms to the Sun's luminosity evolution but spread over a timescale hundreds to thousands of times longer. The rate of luminosity increase per billion years is therefore hundreds to thousands of times slower than the Sun's. Over any timescale accessible to biological evolution, a few billion years at most, the luminosity of an old red dwarf is effectively constant, changing by only a fraction of a percent. The habitable zone of an old red dwarf is stable to a degree that the Sun's habitable zone, slowly shifting outward as the Sun brightens, can never match. One of the most observationally accessible aspects of red dwarf aging is the gradual spin-down of the star as it loses angular momentum to the stellar wind through magnetic braking. Young red dwarfs rotate rapidly, with rotation periods of hours to a few days, the remnant of the rapid rotation acquired during the contraction of the protostellar core when the conservation of angular momentum spun up the collapsing material. As the star ages, the magnetic braking process continuously transfers angular momentum from the star to the outflowing stellar wind, gradually reducing the rotation rate. The spin-down timescale depends sensitively on stellar mass. More massive red dwarfs spin down relatively quickly, reaching the slowly rotating, magnetically quiet state within a few billion years. Less massive red dwarfs spin down more slowly. The least massive red dwarfs, those near the hydrogen burning minimum, may retain rapid rotation for tens of billions of years or more. Current observational surveys including extensive photometric monitoring by the Kepler and TESS space telescopes have revealed that the rotation period distribution of red dwarfs shows a bimodal structure, a population of rapidly rotating active stars with periods of a few days and a population of slowly rotating quiet stars with periods of weeks to months. This bimodality suggests that the spin-down involves a relatively rapid transition at some critical rotation rate, above which the magnetic braking accelerates and the star quickly transitions from fast to slow rotation. The physical mechanism responsible for this transition is not fully understood and is an active area of theoretical investigation. The observational consequence of spin-down is a systematic relationship between the age of a red dwarf and its rotation period, called gyrochronology. For some like stars, gyrochronology is well established. The rotation period is a reliable indicator of age, with older stars rotating more slowly in a predictable way. The calibration of gyrochronology for red dwarfs is an active area of research, complicated by the fact that the spin-down behavior of fully convective red dwarfs differs from that of stars with a tachocline, and by the limited sample of red dwarfs with well-determined ages. But the principle holds: a slowly rotating red dwarf is an old red dwarf, and an old red dwarf is a quiet one. The magnetic activity of a red dwarf, the flaring, the star spots, the chromospheric and coronal emission, the stellar wind strength, all are directly connected to the rotation rate through the magnetic dynamo. As the rotation rate decreases over the star's lifetime, the activity decreases in tandem, and the history of a red dwarf's activity is essentially the history of its spin-down translated into magnetic language. A 1 billion-year-old red dwarf is typically still in its active phase, rotating rapidly, producing frequent flares and maintaining a hot dense corona. A 5 billion-year-old red dwarf may be in the transition zone, its activity declining but still present. A 10 billion-year-old red dwarf is typically in the quiet phase for all but the least massive examples, its flare rate reduced by orders of magnitude, its corona cool and tenuous. The timeline of activity decline has important consequences for any life in the system. Life that can survive the vigorous early active phase and persist into the quiet phase gains access to a habitable environment of extraordinary stability. The transition from active to quiet is therefore a critical threshold in the habitability history of a red dwarf system, analogous in importance to the end of the late heavy bombardment in Earth's early history, after which conditions became sufficiently stable for the persistence of a continuous biosphere. Observations of red dwarfs across a range of ages reveal the activity evolution in real time, not by watching any single star change, but by sampling the distribution of activity levels in a population of stars of known ages. The picture that emerges is one of vigorous early activity for all red dwarfs, followed by a gradual decline extending over billions of years for the more massive red dwarfs and potentially tens of billions of years for the least massive, followed by eventual settling into the quiet state that defines the mature red dwarf. As a fully convective red dwarf ages and its overall hydrogen content decreases while its helium content increases, the structural response is gradual and modest but measurable in principle. The star becomes slightly larger and slightly more luminous over its main sequence lifetime, with the radius increasing by perhaps 10 to 20% and the luminosity increasing by the 20 to 40% mentioned earlier. For a partially convective red dwarf, the structural evolution is more pronounced. With a growing helium core that is not mixed away by convection, the core contracts and heats as the mean molecular weight increases, driving a more significant luminosity increase over the main sequence lifetime. The surface temperature of a red dwarf, its effective temperature, also changes slightly as it ages. For fully convective red dwarfs, the effective temperature changes are small, with the star becoming very slightly warmer as its luminosity increases while its radius increases by a smaller factor. These subtle structural changes over trillion-year timescales are not currently observable directly, because no red dwarf has been watched for long enough to detect the evolution, and the changes per billion years are too small to be detected even in comparisons of red dwarfs of different ages. But they are predicted by stellar evolution models with considerable confidence, and they represent the slow turning of the stellar clockwork that will eventually exhaust the red dwarf's fuel supply. Let us attempt a portrait of a red dwarf far into its future, at an age that no star currently in the universe has reached. Let us imagine the least massive red dwarfs, those near the hydrogen burning minimum at approximately 8% of the solar mass, at the age of 5 trillion years. The universe as a whole is currently 13.8 billion years old. 5 trillion years is approximately 360 times the current age of the universe. At 5 trillion years, the universe is a profoundly different place. The Sun has long since exhausted its hydrogen and ended as a cooling white dwarf. All other Sun-like stars have similarly evolved off the main sequence. The only stars still burning are the red dwarfs, and specifically only those with masses below roughly 20% of the solar mass. A red dwarf of 8% solar mass at 5 trillion years has consumed approximately half of its initial hydrogen supply. It has been burning for a time 500 times longer than the current age of the universe. Its interior is thoroughly homogeneous, well mixed by 5 trillion years of convective overturning, its helium fraction perhaps 30 to 40% by mass. Its surface temperature has changed almost imperceptibly. It is still a deep red star, still glowing in the same color, the same spectral class, the same molecular absorption features in its spectrum. To an outside observer who did not know its age, it would look like any other mid-range red dwarf common in today's galaxy. There is no visible sign of its extraordinary age written on its surface. Its rotation has slowed to perhaps once per month or once per year. Its magnetic activity is minimal, its flare rate close to zero, its corona cool and nearly invisible. The system around it is bathed in a radiation environment quieter than the Earth's today, illuminated by a dim red light that has been streaming outward at nearly constant intensity for 5 trillion years. 5 trillion years. Half the star's life remaining. The same patient burning, the same dim red light, the same fully convective interior stirring its hydrogen and helium in the same slow circulation that has operated continuously since the star ignited. The universe has changed beyond recognition around it, but the red dwarf has not. And still it burns. One of the most remarkable aspects of the red dwarf population in today's Milky Way is the extraordinary range of ages it spans. Because red dwarfs live so long without evolving off the main sequence, every red dwarf ever formed in the Milky Way since the earliest epoch of galaxy formation is still burning today. The galaxy's red dwarf population is a living archive of stellar formation history, containing stars born at every epoch from the first billion years after the Big Bang to stars forming right now in active molecular clouds throughout the disk. The oldest red dwarfs in the galaxy are members of the metal-poor halo population, stars that formed in the first few billion years of the galaxy's history when the interstellar medium was nearly primordial in composition. These ancient red dwarfs, some of them 10 to 12 billion years old, are in the earliest third of their main sequence lifetime. They have changed very little since they formed. They look almost exactly as they did 10 billion years ago. They have watched the galaxy transform around them, from a turbulent irregular system of merging protogalactic fragments to the organized structured Milky Way of today, without themselves changing appreciably. Between the oldest and youngest red dwarfs lies a continuous distribution of ages, a census of every epoch of star formation in the Milky Way's history. Reading the ages of individual red dwarfs through their rotation rates, activity levels, lithium abundances, and kinematic properties is therefore an indirect way of reading the star formation history of the galaxy itself. The red dwarfs are the galaxy's memory. Patient, long-lived, chemically pristine in comparison to their more massive counterparts that have recycled their material through generations of birth and death, they carry the chemical and kinematic fingerprints of the conditions under which they formed, across timescales that span the entire history of the galaxy. They have seen everything the galaxy has done. They will see everything it does for trillions of years to come. They burn on. And in their burning, they remember. Every death is shaped by the life that preceded it. The deaths of the most massive stars are violent and sudden, a supernova blast that tears the star apart in seconds and scatters its material across dozens of light-years of surrounding space, leaving behind either a neutron star spinning at hundreds of revolutions per second or a black hole from which nothing escapes. The deaths of sun-like stars are slower and stranger, a swelling into red gianthood over hundreds of millions of years, an ejection of the outer layers as a planetary nebula of extraordinary beauty, and a contraction of the remaining core into a white dwarf that cools over billions of years toward darkness. Each type of stellar death carries the imprint of the physics that govern the star's life, the nuclear reactions, the structural changes, the thermodynamic constraints that shaped everything from the first ignition to the final darkness. The death of a red dwarf is unlike either of these. It is not violent. It does not produce a supernova or a planetary nebula or a neutron star. It does not swell dramatically or shed its outer layers or leave an object fundamentally different in kind from what came before. The death of a red dwarf is the quietest, most gradual, most undramatic ending in the entire stellar zoo, a slow fading that is the logical conclusion of the slow burning that define the entire main sequence life. But it is a death, nonetheless. A process with a definite endpoint. A transition from the state of hydrogen burning equilibrium that defines the main sequence to a final state that is cold and dark and effectively inert. And the path from the last moment of nuclear burning to that final state is, in its own quiet way, deeply interesting, shaped by physics that differs in important details from the deaths of more massive stars. We are describing an event that has not yet happened anywhere in the universe. Not a single red dwarf has yet died, because not a single red dwarf has yet had time to exhaust its hydrogen. The youngest red dwarfs are a few million years old. The oldest are about 12 billion years old. The least massive red dwarfs will live for 10 trillion years. None of them has reached the end. What follows is therefore necessarily theoretical, a projection of known physics into a future that observation cannot yet reach. But the physics is well understood, and the projection is trustworthy in its broad outlines, if not in every detail. The main sequence lifetime of a red dwarf ends when the hydrogen available for nuclear fusion has been consumed to the point where the nuclear reaction rate can no longer maintain the pressure support required to prevent gravitational collapse. For a fully convective red dwarf, this moment arrives not when the core hydrogen is exhausted, as it does for the Sun, but when the overall stellar hydrogen fraction has declined to a level below which the fusion rate across the entire well-mixed stellar volume is insufficient. The approach to hydrogen exhaustion in a fully convective red dwarf is gradual and lacks the dramatic structural transitions that mark the Sun's departure from the main sequence. In the Sun, core hydrogen exhaustion triggers the development of a hydrogen-burning shell around the growing helium core, which drives the rapid luminosity increase and radius expansion that characterize the subgiant and red giant phases. In a fully convective red dwarf, there is no distinct core-to-shell transition because there is no compositionally distinct core. The entire star simply runs low on fuel simultaneously, with the nuclear reaction rate declining uniformly throughout the stellar volume as the overall hydrogen abundance decreases below the threshold for sufficient energy production. As the hydrogen abundance falls towards zero over the final few percent of the stellar lifetime, the nuclear energy generation rate declines. The reduced energy input means reduced pressure support, and the star begins to contract slightly under gravity. The contraction releases gravitational energy, partially compensating for the reduced nuclear energy and slowing the luminosity decline. But the contraction also raises the central temperature, and the rising temperature increases the reaction rate for whatever hydrogen remains, accelerating its consumption. The approach to hydrogen exhaustion is therefore a self-accelerating process in its final stages, as the star contracts, heats, burns its remaining hydrogen faster, and contracts further. The final hydrogen burning in a red dwarf occurs at temperatures slightly higher than the main sequence core temperature, driven by the gravitational contraction that supplements the declining nuclear energy source. The last fusion reactions take place in a stellar interior that is hotter, denser, and more compact than the main sequence star, consuming the very last traces of hydrogen in a brief, elevated temperature phase before the fuel is truly exhausted and the nuclear burning ceases entirely. When the last proton-proton reaction occurs and the nuclear fire goes out for the last time, the red dwarf crosses a threshold. It is no longer a star in any meaningful physical sense. It is a contracting ball of helium plasma, without any energy source other than the gravitational energy released by its continuing contraction, heading toward the final state that quantum mechanics and gravity between them decree. One of the most counterintuitive predictions of stellar evolution theory for red dwarfs is that, as they approach the end of their main sequence lives and begin to exhaust their hydrogen, they do not become redder and larger, as sun-like stars do when they evolve toward the red giant branch. Instead, the fully convective red dwarfs are predicted to become bluer and more luminous, briefly, before declining toward their final fate. This blue dwarf phase, sometimes called the blue phase of red dwarf evolution, arises from the same physics that makes fully convective stars evolve differently from partially radiative ones. As the overall hydrogen abundance of the fully convective star decreases, the opacity of the stellar interior decreases as well, because hydrogen-rich plasma is more opaque than helium-rich plasma at the temperatures found in red dwarf interiors. The decreasing opacity allows radiation to transport energy more efficiently, which changes the thermal structure of the star in a way that makes the outer layers hotter rather than cooler. The result is that a red dwarf approaching the end of its main sequence life actually increases in surface temperature, gradually shifting its spectral type from M toward K and eventually toward G as the helium fraction rises and the surface temperature climbs. The luminosity also increases, driven by both the higher surface temperature and the slight increase in radius. At the peak of the blue dwarf phase, a red dwarf that spent trillions of years as a dim, cool, deep red M dwarf may briefly resemble a slightly undersized sun-like star, with a yellow-white color and a luminosity comparable to the present sun's. The blue dwarf phase is temporary. It lasts for perhaps a few tens to hundreds of billions of years, a long time by any ordinary measure but a fraction of the star's main sequence lifetime. After the peak of the blue dwarf phase, as the hydrogen is finally exhausted and the nuclear burning ceases, the star contracts toward its final state and its luminosity declines, though the surface temperature may remain elevated for some time as the contracting surface area compensates for the declining luminosity per unit area. The blue dwarf phase has interesting implications for the habitability of planets around aging red dwarfs. A planet that orbited in the habitable zone of its red dwarf host for trillions of years of stable, Dim, red illumination would find itself increasingly irradiated as its star brightened and warmed into the blue dwarf phase. The habitable zone would migrate outward as the stellar luminosity increased, potentially rendering previously habitable planets too hot for liquid water while simultaneously bringing previously frozen outer planets into the habitable zone for the first time. The blue dwarf phase represents a final window of habitability migration in the red dwarf system, one that any life that had persisted through the long quiet main sequence would need to adapt to or perish. After the blue dwarf phase ends and the hydrogen fuel is completely exhausted, the former red dwarf, now a ball of nearly pure helium plasma, contracts under gravity. It cannot initiate helium fusion. Helium fusion, the triple alpha process that fuses 3 helium nuclei into carbon, requires core temperatures of approximately 100 million Kelvin, far above the temperatures achievable by the contraction of a low-mass stellar remnant. The less massive the object, the lower the temperature it reaches upon gravitational contraction before quantum mechanical pressure, specifically the electron degeneracy pressure that also halted the brown dwarf contraction at an earlier stage, intervenes to stop the collapse. For a red dwarf remnant, the gravitational contraction compresses the helium until the electron gas becomes degenerate, with the quantum mechanical pressure of the compressed electron gas providing the pressure support against further gravitational collapse. The object has become a white dwarf, not the carbon-oxygen white dwarf that is the remnant of a Sun-like star's core, but a helium white dwarf, composed almost entirely of helium-4 with trace amounts of any elements heavier than helium that were present in the initial red dwarf composition. Helium white dwarfs are rare in today's universe, for the simple reason that producing one requires a star to exhaust its hydrogen on the main sequence, which requires a main sequence lifetime shorter than the current age of the universe, which in turn requires a minimum mass significantly above the red dwarf range. The helium white dwarfs that do exist today were produced not by red dwarf evolution but by binary star interactions, in which mass transfer from one star to another stripped the hydrogen envelope from a star that would otherwise have evolved into a red giant, leaving behind a helium core that became a helium white dwarf prematurely. These binary-produced helium white dwarfs are useful analogs for understanding the properties of the helium white dwarfs that will eventually be produced by single red dwarf evolution, but they are formed by a fundamentally different process. The helium white dwarf produced by a red dwarf at the end of its main sequence life will have a mass comparable to the original red dwarf mass, because very little material is lost during the evolution. Unlike a Sun-like star, which loses a significant fraction of its mass in the stellar wind during the red giant phase and the planetary nebula ejection, a red dwarf loses very little mass over its entire main sequence lifetime. The stellar wind is weak, the surface is not expanded to giant dimensions, and there is no dramatic mass ejection event. The white dwarf inherits essentially the entire mass of the original red dwarf, packed into an object the size of the Earth. The density of this helium white dwarf is enormous. A mass comparable to the original red dwarf, perhaps 10% of the solar mass, compressed into a volume comparable to the Earth's, gives a density millions of times greater than water. The surface gravity is immense. The surface temperature at formation, heated by the gravitational contraction, is moderate by white dwarf standards, perhaps 10,000 to 30,000 Kelvin, giving the newly formed helium white dwarf a bluish-white appearance very different from the deep red of its main sequence progenitor. The newly formed helium white dwarf, emerging from the final contraction of the hydrogen-exhausted red dwarf remnant, begins its own long journey toward darkness. It has no nuclear energy source. It cannot fuse helium. It cannot generate energy by any nuclear process. The only energy available is the thermal energy stored in the compressed helium nuclei of its interior, the heat of the gravitational contraction and the residual thermal energy of the stellar interior that was never radiated away. That thermal energy will now be radiated slowly away from the white dwarf surface, cooling the object over billions and trillions of years as it slowly dims and reddens, descending through the spectral sequence from the hot blue-white of a newly formed white dwarf toward the cool red of a very old, very cold one, and eventually toward the theoretical black dwarf that is the cold, dark endpoint of the cooling sequence. The cooling rate of a white dwarf depends on its mass, its composition, and its surface temperature. More massive white dwarfs are smaller, with higher surface gravity and smaller surface area relative to their thermal energy content, and they cool more slowly per unit energy than less massive ones. Helium white dwarfs cool at a rate that depends on the specific heat of the helium interior and the opacity of the thin hydrogen and helium layer that forms the surface. The detailed cooling curves have been computed by stellar evolution modelers and show that a helium white dwarf of typical red dwarf remnant mass will cool to below 10,000 Kelvin surface temperature in a few billion years, below 5,000 Kelvin in tens of billions of years, and continue declining toward temperatures approaching absolute zero over trillions of years. As the white dwarf cools below approximately 12,000 Kelvin, the helium in the interior begins to crystallize, transitioning from a liquid plasma state to a solid, crystalline lattice. The crystallization releases latent heat, slowing the cooling temporarily and causing the white dwarf to linger at a nearly constant temperature for an extended period while the latent heat is radiated away. This crystallization delay, detected observationally in the population of cool white dwarfs in the solar neighborhood through a statistical excess of white dwarfs at the expected crystallization temperature, will also occur in red dwarf helium white dwarfs as they cool through the crystallization regime. After crystallization is complete and the latent heat has been radiated away, the cooling resumes, with the crystalline helium interior now cooling more slowly because crystalline solids have lower specific heats than liquid plasmas at the same temperature. The white dwarf becomes, in its final billions of years of detectable existence, a cold, dense, crystalline ball of helium ice, solid throughout, radiating the last of its thermal energy from a surface that glows ever more dimly in the infrared. Eventually, on timescales of many trillions of years, the helium white dwarf descendant of a red dwarf will cool below any temperature at which it emits detectable radiation. It becomes a black dwarf, an object that is cold, dark, and inert, present in the universe but undetectable by any means that depends on its electromagnetic emission. It will continue to exist, dense and compact, drifting through whatever space remains of the galaxy or the larger universe, a cold memorial to the patient star that burned for trillions of years before finally going dark. One of the most visually striking phenomena in all of astronomy is the planetary nebula, the expanding shell of gas ejected by a dying sun-like star as it sheds its outer envelope during the asymptotic giant branch phase of evolution. The planetary nebulae of sun-like stars are among the most beautiful objects in the sky, They're glowing shells of ionized gas sculpted by the interaction of the fast post-asymptotic giant branch wind with the slower material ejected earlier, illuminated by the ultraviolet radiation of the hot white dwarf at their center, forming structures of extraordinary variety and complexity including rings, bipolar lobes, jets, and concentric shells. The death of a red dwarf produces none of this. There is no asymptotic giant branch phase, no thermal pulses, no dredge-up of carbon from the interior, no superwind that sheds the outer envelope. The red dwarf does not expand to giant dimensions. It does not develop a degenerate helium core with a hydrogen-burning shell above it. It simply exhausts its hydrogen gradually, heats slightly, and brightens briefly in the blue dwarf phase, and then contracts directly to a white dwarf without any dramatic mass ejection event. The surrounding space of a dying red dwarf remains clean and empty. No expanding shell of illuminated gas marks its passage from main sequence star to white dwarf. No glowing nebula catches the ultraviolet light of the newly formed white dwarf and broadcasts the star's death across the galaxy. The transition is invisible from a distance. A red dwarf that was burning trillions of years ago simply becomes a white dwarf, and the only way to know that the transition has occurred is to look carefully at the point of light that was once the red dwarf and notice that it has changed its color and luminosity in the way that white dwarfs differ from main sequence red dwarfs. This quiet departure is entirely consistent with the red dwarf's character. Patient in life. Patient in death. No dramatic gestures. No spectacular final performance. Just the steady, gradual, unhurried transition from one stable state to another, carried out over billions of years, leaving the surrounding universe exactly as undisturbed as the star's entire life had left it. The contrast with the supernova deaths of massive stars could not be more complete. A core-collapsed supernova releases in a few seconds more energy than the Sun will radiate in its entire 10 billion-year lifetime, scattering heavy elements across hundreds of light-years, compressing nearby molecular clouds with its shockwave and potentially triggering new star formation, leaving behind either a rapidly spinning neutron star pulsing in X-rays and radio waves or a black hole consuming whatever comes within its gravitational reach. The supernova announces itself to the universe. It makes its mark. It cannot be ignored. The death of a red dwarf is a whisper. A gradual dimming. A slow shift of color from red to white as the surface temperature of the cooling remnant replaces the surface temperature of the burning star. And then silence. When a red dwarf finally exhausts its hydrogen and begins the transition to a white dwarf, whatever existed in its planetary system faces the consequences. The planets do not disappear. Gravity holds them in their orbits. The rocky worlds, the water worlds, the tidally locked spheres that orbited in the habitable zone for trillions of years, they continue to orbit the white dwarf remnant. But the conditions on their surfaces change radically and permanently. The white dwarf that forms from a red dwarf is initially hot, but it is also tiny, barely larger than the Earth, and its luminosity drops precipitously in the billions of years after formation. The habitable zone of a newly formed helium white dwarf, if such a thing can be defined, would be extremely close to the white dwarf, at distances of a fraction of an astronomical unit, where the tiny but hot remnant delivers sufficient energy for liquid water. But the planets of the original red dwarf system were orbiting at distances calibrated to the red dwarf's luminosity, not the white dwarfs. As the white dwarf forms and then cools, the luminosity drops rapidly, and the planets that were in the red dwarf's habitable zone find themselves now in a frigid, dark environment, receiving tiny fractions of the energy they once received. For any life that existed on those planets during the red dwarf's main sequence, the death of the star is ultimately fatal. Not immediately, not in any single catastrophic event, but over the billions of years of the blue dwarf phase and the subsequent formation and cooling of the white dwarf, the habitable conditions that sustained life through trillions of years of patient red light are systematically dismantled. The oceans freeze. The atmosphere collapses. The last energy gradient available to drive biological metabolism fades below the threshold of biological utility. Life, if it existed, ends. It ends not with a bang but with a long, slow, deepening cold. The planets continue to orbit the cooling white dwarf, silent and frozen, for the remainder of the universe's history. They are dark now, their surfaces iced over, their atmospheres frozen to the ground, carrying in their geology and chemistry the record of the trillions of years of life and activity that once characterized them. The record is there. Unreadable, in any practical sense. But present. The universe does not erase its history. It buries it under cold and darkness and time. In the far future, when the last red dwarfs have finally exhausted their hydrogen and contracted to white dwarfs, the universe will contain an extraordinary population of cold, dark helium white dwarfs, the accumulated remnants of every red dwarf that ever burned in every galaxy that ever formed. This population will vastly outnumber the carbon-oxygen white dwarfs produced by sun-like stars, simply because red dwarfs outnumber sun-like stars by roughly 10 to 1, and because every red dwarf eventually produces exactly one white dwarf. The mass budget of baryonic matter in the universe's far future will be dominated by these white dwarf remnants. The gas in galaxies will have long since been consumed by star formation or expelled by feedback, leaving no raw material for new stars. The stars themselves will have evolved off the main sequence and contracted to white dwarfs or neutron stars or black holes. The baryonic matter of the universe, the ordinary matter made of protons and neutrons and electrons, will be packed into these compact objects, with the white dwarfs containing the vast majority of it by number and a substantial fraction by mass. This white dwarf graveyard will cool over timescales comparable to the current age of the universe per few Kelvin of temperature drop, slowly dimming from the hot blue-white of newly formed remnants to the warm white of middle-aged ones to the cool yellow and orange of old ones, and eventually to the theoretical black dwarfs that represent the thermodynamic endpoint of white dwarf cooling. The timescale for the coolest white dwarfs currently observable to reach black dwarf temperatures is estimated at roughly 10 to the 15th years, a quadrillion years, far beyond the current age of the universe but well within the range of the red dwarf lifetimes we have been discussing. The universe is patient. The red dwarfs are patient. And the remnants they leave behind are patient still, cooling at their glacial pace toward the ultimate cold, carrying their compressed helium and their frozen surfaces and their silent orbiting planetary systems through the darkening future of a universe that has exhausted its brightest lights and is settling, slowly, into the dim remnant glow of the last cooling fires. The red dwarf lives for trillions of years and dies without drama, and its legacy is a cold white sphere no larger than the Earth, orbited by frozen worlds, drifting in the growing dark between the last stars. There is something beautiful in that. Something deeply, quietly beautiful. There will come a time, incomprehensibly distant from now, when the last massive star in the observable universe has exploded. When the last sun-like star has swelled into a red giant and shed its outer layers and contracted to a white dwarf. When the last of the orange and yellow K-dwarfs has followed the same path and left its own white dwarf remnant. When the stellar sky, once rich with the light of hundreds of billions of stars and hundreds of billions of galaxies, has gone dark in all but the faintest, dimmest, most patient fires. That time is not yet. We are living in the universe's golden age, the era of stars, the luminous epoch that began a few 100 million years after the Big Bang with the ignition of the first stars, and that will end, in astronomical terms, relatively soon. In roughly 100 trillion years, the last sun-like star will have exhausted its hydrogen. The main sequence will be empty of all but red dwarfs. And the universe will enter a new phase of its history, one that is defined not by the brilliant diversity of stellar types we observe today but by the slow, patient, dim burning of the smallest fires. The red dwarfs will be the last stars. Not metaphorically but literally. When every other kind of star has finished its nuclear burning and left its remnant, the red dwarfs will still be on the main sequence, still fusing hydrogen to helium, still illuminating whatever planets orbit them with their dim red light. They will burn alone in a universe that has otherwise gone dark, the final torches of the stellar era, maintaining the conditions for warmth and light and possibly for life on their slowly cooling surfaces for trillions of years after the last sun has set forever. Cosmologists who study the long-term future of the universe have divided it into a series of eras defined by the dominant physical processes operating in each. The current era, stretching from roughly 1 million years after the Big Bang to roughly 100 trillion years in the future, is called the stelliferous era, the age of stars. It is the era in which nuclear fusion in stellar cores provides the dominant energy source for luminous matter in the universe, in which the complex interplay of stellar birth, evolution, and death drives the chemical enrichment of galaxies and the formation of planets and the development of biology, and in which the universe is bright enough, warm enough, and chemically complex enough to support the emergence of life and intelligence. We are, right now, approximately 14 billion years into the stelliferous era, which will last roughly 100 trillion years in total. In the proportional terms of this era's lifetime, we are at roughly the first 1/10,000th of its duration. The stelliferous era has barely begun. The vast majority of its history lies in the future, a future dominated by the slow burning of the red dwarfs. The most massive stars, the O and B giants that blazed so brilliantly in the early universe and that continue to form and die in active star-forming regions today, have lifetimes of only a few million years. They have been forming and dying throughout the stelliferous era, cycling their material through successive generations, enriching the interstellar medium with the heavy elements they synthesize and scatter. But they are temporary. By 10 billion years from now, the formation of new massive stars will be increasingly suppressed as the supply of cold molecular gas in galaxies is consumed and the remaining gas is heated by feedback from the last generations of active star formation. The era of massive star formation is already past its peak and is declining. The Sun-like G and K stars, with lifetimes of 10 to 50 billion years, will continue forming and evolving for tens of billions of years into the future before the gas supply is exhausted. The last Sun-like star is estimated to form roughly 100 trillion years from now, after which no new Sun-like or more massive stars will ignite anywhere in the universe. From that point, the main sequence will be inhabited only by the red dwarfs that formed earlier and are still burning, slowly depleting as they too exhaust their hydrogen over the following trillions of years. The last red dwarf to exhaust its hydrogen and transition to a white dwarf will do so approximately 10 trillion years from now, give or take a few trillion depending on the distribution of red dwarf masses and the efficiency of their hydrogen burning. After that, the stelliferous era is definitively over. The universe enters the degenerate era, dominated by the cooling white dwarfs and neutron stars and black holes that are the remnants of the stellar era, with no new nuclear burning occurring anywhere. Between now and that ending, the red dwarfs burn. Patient, dim, red, alone in the growing dark. The last torches of an era that produced everything we know. Imagine the universe 1 trillion years from now. 10 times the age of the universe at the death of the last Sun-like star, but still within the lifetime of the longest-lived red dwarfs. The universe at this epoch is profoundly different from the one we inhabit, and its most striking feature is the near-total absence of the kinds of stars that dominate our current sky. The brilliant blue supergiants are gone, have been gone for hundreds of billions of years. The sun itself is gone, long since a cooling white dwarf somewhere in the diffuse stellar halo of the Milkomeda merger. The Milky Way and Andromeda have long since merged and settled, their combined stellar population of billions of sun-like stars all having evolved off the main sequence and joined the growing population of white dwarfs. The beautiful spiral structure that the Milky Way displayed for its entire 11 billion year history has been erased by the merger, replaced by the smooth, featureless light distribution of an old elliptical galaxy. In this future galaxy, the remaining visible stars are almost entirely red dwarfs. Their dim red-orange light, individually too faint to see without instruments, collectively provides a faint background glow that is the galaxy's last sustained luminosity. No new stars are forming. The molecular gas that once fueled star formation has been consumed or heated and dispersed, and the galaxy is slowly using up its remaining stellar fuel without replenishment. The total luminosity of the galaxy is a tiny fraction of what it was in the current epoch, reduced by orders of magnitude as the bright, hot stars have been replaced by the dim, cool ones. The sky from a planet orbiting one of these trillion-year-old red dwarfs would be extraordinary in its emptiness. The nearby stars, all red dwarfs, would appear as extremely faint reddish points requiring optical aid to see clearly. The Milkomeda galaxy itself might provide a faint background glow along the plane, but the spectacular star-forming nebulae and young star clusters that punctuate the current Milky Way would be completely absent. The universe is darker at 1 trillion years than it is today, and it will only continue to darken as more and more red dwarfs exhaust their hydrogen and join the growing population of cold white dwarfs. And yet, in that dim and quiet universe, some of the red dwarfs are still burning with the same steady fire they have maintained for their entire multi-trillion-year lives. Their light is dim. Their planets, if they survive the long evolution of the stellar system through 1 trillion years of orbital dynamics and tidal evolution and episodic bombardment from the debris of countless dead systems, are perhaps still warmed by that light. Perhaps still, in some narrow band of temperature between ice and boil, harboring the conditions for liquid water and whatever chemistry requires. Perhaps still alive with something. Somewhere in the universe, far in the future, the last red dwarf will burn. Not the last red dwarf in existence, because white dwarfs that were once red dwarfs will persist for far longer. But the last red dwarf still on the main sequence, still fusing hydrogen to helium in its slowly convecting interior, still illuminating its surrounding space with the dim red light that has been the signature of this stellar class since the first red dwarf ignited. This last burning red dwarf will be among the least massive of its kind, a star very close to the hydrogen burning minimum, burning its fuel with the maximum possible conservation, extending its life to the furthest limit that stellar physics permits. It may have formed relatively recently in cosmic terms, from a last whisper of star-forming gas in some corner of a galaxy that has long since exhausted most of its molecular cloud material. Or it may be among the oldest red dwarfs, a survivor from the early universe that has been burning for essentially the entire history of the stelliferous era. When this last red dwarf finally exhausts its hydrogen and begins the transition to its helium white dwarf remnant, the stelliferous era ends. Not with an announcement. Not with any observable signal that propagates through the universe to mark the moment. Just with the final dimming of the last nuclear fire, the last proton-proton reaction in the last stellar core, and the beginning of a silence that will last, in the forms we have explored in earlier journeys, for trillions upon trillions of additional years. The red dwarfs are the keepers of the flame. They are the stars that carry the stelliferous era as far as physics will carry it, burning patiently through epochs that no other stellar type could survive, maintaining the conditions for light and warmth in a universe that is otherwise darkening around them. They are not the most spectacular stars. They are not the most chemically productive, not the most energetic, not the most visible. But they are the most persistent. And in the long run, persistence is the most remarkable quality of all. The chemical history of the universe is written in the compositions of its stars and the interstellar medium that connects them. Every element heavier than hydrogen and helium was produced by nuclear burning in stellar interiors or by explosive nucleosynthesis in supernovae and neutron star mergers, and returned to the interstellar medium through stellar winds, planetary nebulae, supernova ejecta, and the other mass loss processes that accompany stellar death. The universe has enriched itself in heavy elements over its entire history through this cycle of stellar birth, nucleosynthesis, death, and recycling. Red dwarfs, despite their enormous numbers, contribute relatively little to this heavy element enrichment cycle. They do not produce heavy elements in significant quantities, because their core temperatures are too low for any nucleosynthesis beyond the proton-proton chain's production of helium. They do not return their material to the interstellar medium during their main sequence lives, because their stellar winds are weak and their mass loss rates are negligible. And when they die quietly, contracting to white dwarfs without the explosive nucleosynthesis of a supernova or the chemically enriched wind of an asymptotic giant branch star. The heavy elements locked inside red dwarfs at their formation are, in effect, removed from the chemical cycle for the duration of the red dwarf's lifetime, which is to say for trillions of years. A red dwarf that formed in the early universe with a small but non-zero metallicity has been holding that metal content in its interior, inaccessible to the interstellar medium and to subsequent generations of star formation, for 10 to 12 billion years. When it eventually dies and becomes a white dwarf, those metals will be incorporated into the white dwarf's thin surface layer or remain locked in the interior, still largely inaccessible. In this sense, the red dwarfs are accumulators rather than recyclers. They gather the chemical products of previous stellar generations at their formation, and they hold onto them for trillions of years. The heavy elements in the red dwarfs are, for the duration of the stelliferous era, sequestered in these long-lived objects, waiting patiently for the eventual cooling of their white dwarf remnants to release them, over astronomical timescales, into whatever medium surrounds them. The universe's chemical evolution, the gradual enrichment of the interstellar medium and heavy elements over cosmic time, is dominated by the short-lived massive stars that form, synthesize heavy elements rapidly, and die in supernovae on timescales of millions of years. The red dwarfs participate in this story not as drivers but as archives, holding within them the chemical composition of the universe at the moment of their formation, carrying that record forward through the billions and trillions of years of their patient burning. Despite being the most common type of star in the universe, the census of red dwarfs in the solar neighborhood is still incomplete. The faintest red dwarfs, those at the low-mass end of the stellar sequence near the hydrogen-burning minimum, are so dim that even nearby examples at distances of a few light-years would be challenging to detect with current survey instruments without dedicated effort. The completeness of the red dwarf census drops off rapidly beyond distances of a few tens of light-years, and beyond a few hundred light-years our knowledge of the red dwarf population is statistical rather than individual. New and upcoming observational programs are progressively improving the census. The Gaia space mission, which has measured precise parallaxes, proper motions, and photometric colors for over 1 billion stars in the Milky Way, has dramatically expanded the known population of red dwarfs within a few hundred light-years of the Sun and has revealed new subclasses, companions, and kinematic properties that were previously inaccessible. Dedicated red dwarf surveys in the near-infrared, where red dwarfs emit most of their light, have pushed the census to greater distances and lower masses. The planet census around red dwarfs is similarly incomplete but rapidly improving. Transit surveys including the Kepler, K2, and TESS missions have discovered hundreds of red dwarf planetary systems and have begun to characterize the occurrence rates and size distributions of red dwarf planets with statistical rigor. Radial velocity surveys with new high-precision spectrographs designed specifically for the near-infrared wavelengths where red dwarfs are brightest have detected dozens of red dwarf planets and are pushing the detection threshold toward Earth-mass objects in habitable zones. Direct imaging of red dwarf circumstellar environments and debris disks is revealing the architecture of mature red dwarf planetary systems in ways that complement the transit and radial velocity detections. The picture that is emerging from these surveys is one of extraordinary planetary richness. Red dwarfs host planets at high rates, with multiple planet systems being common and rocky planets in the habitable zone being among the most frequent planet types detected. The fraction of red dwarfs with at least one Earth-sized planet in the habitable zone is estimated at roughly 20 to 30% based on current survey completeness. Extrapolated to the full Milky Way red dwarf population, this implies billions of potentially habitable rocky worlds orbiting red dwarfs in our galaxy alone. Billions of worlds, lit by dim red suns, waiting, as the red dwarfs wait, in the patient arithmetic of stars and time. We have spent 3 hours in the company of the red dwarfs, and I want to close not by summarizing what the physics has taught us, which you carry now in the way that slowly absorbed knowledge settles into the body rather than the mind, but by saying something about what it feels like to have sat with these stars through the length of this journey. There is a particular quality of attention that the red dwarfs invite. Not the breathless wonder of the supernova, not the existential vertigo of the black hole, not the gorgeous complexity of the spiral galaxy seen from above. Something quieter. Something more interior. A quality of attention that resembles, more than anything else, the particular awareness one has in the middle of the night when everything is still and the mind is neither fully asleep nor fully awake, when the ordinary dimensions of time and consequence have softened and the longer rhythms of things are briefly accessible. The red dwarfs live in those longer rhythms. They are the stars of the long view. And in sitting with them for these 3 hours, something of their patience has perhaps been transferred, the way the temperature of a room is transferred to anyone who sits in it long enough. The most immediate lesson of the red dwarfs is about patience and its relationship to duration. The red dwarf burns slowly because it is small. It burns slowly because its core temperature is barely sufficient for nuclear fusion. It burns slowly because the proton-proton chain, already the slowest nuclear reaction in the stellar zoo, operates at the absolute minimum rate that can sustain stellar equilibrium. Everything about the red dwarf is calibrated to the minimum. The minimum luminosity. The minimum temperature. The minimum rate of fuel consumption. And because it burns at the minimum, it burns for the maximum. The relationship is precise and physical. The lifetime of a star on the main sequence is proportional to the fuel supply divided by the fuel consumption rate. Reduce the consumption rate while keeping the fuel supply comparable as a fraction of stellar mass, and the lifetime increases in direct proportion. The red dwarf lives 1 trillion years because it burns its fuel 1 trillion times more slowly than the most extravagant stars. There is no shortcut. There is no trick. There is just the physics of patience, playing out over timescales that dwarf every other process we can name. In human terms, this lesson is difficult to apply directly. We are not red dwarfs. We cannot choose to slow our metabolic rate by a factor of 1 trillion and thereby extend our lives by the same factor. Our biology runs on timescales set by biochemistry and cellular physics, and those timescales are what they are. We cannot be patient in the way a red dwarf is patient, because our patience is measured in years and decades and the red dwarfs is measured in trillions of years. But the lesson of the red dwarf is not meant to be applied literally. It is meant to be contemplated as a perspective. A reminder that the scale of time we experience is long, the decades of a human life, the centuries of a civilization, the millions of years of a species, is a vanishingly brief episode in the full sweep of cosmic time. That the universe is not in a hurry. That the processes that matter most, the ones that shape the largest structures and leave the most enduring records, are frequently the slowest ones. That burning brightly is not the only way to matter. The second lesson of the red dwarfs is about abundance and its relationship to significance. The red dwarfs are everywhere. They are the default star, the typical star, the star that the universe produces most readily and most prolifically whenever the conditions for star formation are met. They are so common that their very commonness has, for most of astronomical history, made them seem unimportant, background objects unworthy of the attention devoted to the spectacular, the rare, the dramatic. But what is common is not unimportant. The red dwarfs are common because the physics of molecular cloud fragmentation preferentially produces them, and that preferential production reflects something fundamental about how gravity and turbulence in quantum mechanics interact at the scales relevant to star formation. Their commonness is not an accident. It is a physical inevitability, written into the equations that govern the collapse of gas under its own gravity. The universe is telling us something by making red dwarfs so much more numerous than any other stellar type, and what it is telling us is that patience and economy are the universe's preferred operating mode. The red dwarfs matter not despite their commonness but because of it. Their sheer numbers mean that even a small probability of habitability per star translates into billions of potentially inhabited worlds. Their long lifetimes mean that the habitable window on any red dwarf world is vast beyond anything we can currently imagine in biological or evolutionary terms. Their chemical stability means that the environments they provide for planets change only infinitesimally over the timescales relevant to biological evolution. When we look at the sky and see the bright, hot, spectacular stars, we are seeing a biased sample of the stellar population, selected by our eye's sensitivity and by the luminosity function that makes bright stars easy to see from great distances. The true composition of the universe's stellar population is dim and red and patient and abundant beyond counting. The sky that represents reality is not the spectacular sky visible to the naked eye but the infrared sky of the red dwarfs. A sky of billions upon billions of small cool fires that our ancestors could not see and that we have only recently learned to appreciate. Looking up at the night sky differently, knowing what is there that our eyes cannot see, is one of the gifts that astronomy gives us. The red dwarfs are there, all around us, in every direction. Proxima Centauri at 4.24 light-years. Barnard's star at 5.96. Wolf 359 at 7.86. Dozens more within 20 light-years. Hundreds within 50. Billions in the galaxy. Hundreds of billions times trillions in the observable universe. All burning. All patient. All waiting for us to notice them. The third lesson of the red dwarfs is about the place of sun-like stars, and by extension the Earth and humanity, in the larger context of stellar diversity. The sun is not typical. It is not the kind of star the universe preferentially produces. It is not the default. It is an exception, a star in the upper quartile of stellar masses, significantly more luminous and significantly shorter-lived than the vast majority of stars in the galaxy. We evolved around a sun because the sun exists and is reasonably hospitable, not because the universe arranged itself specifically for our benefit or because sun-like stars are particularly common. The conditions under which Earth life emerged, the particular combination of stellar type, orbital distance, planetary size, atmospheric composition, geological activity, and cosmic timing, are not guaranteed to be the only conditions under which life can emerge. They are the conditions that worked once, in one place. The universe, with its billions of red dwarfs and their trillions of years of potential habitability, is running an enormous number of other experiments simultaneously, under different conditions, on different timescales, in different corners of the galaxy. We do not yet know the results of those experiments. We may not know for centuries or millennia. But the experiments are running, continuously, in the patient red light of the most common stars. The humility that the red dwarfs invite is not a diminishment of humanity or of the Earth or of the extraordinary fact of our existence. It is a widening, a recognition that our particular path to consciousness and wonder, through a sun-like star and a rocky planet and 4 billion years of biological evolution, is one path among potentially many, and perhaps not even the most probable one. The most probable path to life in the universe, if the probability argument is taken seriously, runs through red dwarfs, through tidal locking, through dim red light, through trillion-year habitable windows that we cannot currently imagine in biological terms because we have only one example and it is not from a red dwarf. The red dwarfs invite us to hold our particular existence lightly. Not dismissively, but lightly. With the awareness that the universe is larger and more diverse and more patient than our single example can fully encompass. Tonight, wherever you are, the nearest red dwarf is Proxima Centauri, approximately 40 trillion kilometers away, completely invisible without a telescope, burning with a luminosity 1,000th of the sun's, illuminating with its dim red light a planet that orbits it every 11 days at a distance so close that the planet is almost certainly tidally locked, always showing the same face to its small red sun. Proxima Centauri has been burning for 4.5 billion years, exactly as long as the sun. It has changed almost imperceptibly in that time. Its surface looks today almost exactly as it looked when the first single-celled organisms were beginning their experiments with photosynthesis in Earth's early oceans. It will look almost the same 4 trillion years from now, when the sun has long since gone cold and whatever descendants of whatever life persists on Earth or its successors are living under different stars. The red dwarfs are the most enduring fires in the universe. Not the most brilliant, not the most productive of heavy elements, not the most spectacular in their deaths. Just the most enduring. The fires that are still burning when everything else has gone out. There is something worth contemplating in that, on a night when you are settling into rest, when the small fires of your own body's metabolism are banking toward the slower rhythms of sleep, when the urgencies of the day have receded and the longer view briefly becomes accessible. You are made of atoms forged in stars, as we have said before and say again now because it bears saying. You are made of atoms that were in stellar cores, some of them in the cores of red dwarfs that are still burning tonight, others in the cores of stars that exploded billions of years ago and scattered their material into the molecular cloud that eventually formed the sun and the earth. The iron in your blood was forged in supernovae. The carbon in your cells was forged in stellar interiors. The hydrogen in the water in your body is primordial, dating to the first few minutes after the Big Bang, before any stars existed. You are the universe examining itself. A temporary arrangement of atoms that has become aware of the arrangement and curious about its origins. And the origins lead back, always, to the stars, to the brilliant ones and the quiet ones, to the short-lived ones and the patient ones, to the supergiants that burned for a few million years and scattered their heavy elements into the next generation, and to the red dwarfs that have been burning since before the Earth existed and will still be burning long after it is gone. The red dwarfs are patient. You can be patient too, for these few hours of darkness, in the way that the body knows how to be patient when it is given permission. Let the breath slow. Let the weight of the body settle into whatever surface holds it. Let the mind release the scale of the day and expand, gently, toward the larger scales we have been contemplating tonight. The scale of the red dwarf's trillion-year lifetime. The scale of the universe at 1 trillion years, dim and quiet and patient. The scale of the smallest fire, burning in the dark at 40 light years, burning tonight, having burned every night of every human life that has ever been lived. Proxima Centauri is burning right now. Barnard's star is burning right now. Wolf 359 is burning right now. Billions upon billions of small red fires, burning in the dark in every direction, patient beyond any patience we can consciously hold, enduring beyond any endurance we can physically achieve, illuminating their worlds with a light that our eyes cannot see, but that is there nonetheless, steady and dim and permanent and real. Sleep in that light. Rest in the long burning of the smallest stars. They will still be there when you wake.